Okay, so let's start. Good morning, everyone, and I welcome all of you to the 39th meeting of the Astronomical Society of India and the workshop 1, which is on computational astrophysics and emerging avenue for Indian astronomy community. I would like to welcome all the participants who have joined the Zoom channel and all those who are also connected through the YouTube link which we have shared, where this whole workshop will be live streamed. It is rapidly growing and into a very much bigger sizable community. The primary aim essentially of this workshop is to bring together such researchers from within and outside of India for exchange of ideas, which will foster collaborations as we move on in the longer run. The main focus of this workshop is to showcase the current and the diverse expertise of the Indian researchers in the field of computational astrophysics. And we hope that this workshop will actually will both sow the seeds for the future and major endeavors in the community and larger gatherings and foster an environment of computational modeling of astrophysical environments. The main aim, you can say the goal of this workshop is mainly to provide an encouragement to young masters and PhD students who are most of our participants to dive into this arena of computational modeling and making them aware of the recent developments, both in national and international front in the area of computational astrophysics. So here, this whole workshop will be divided into 4 different sessions. We begin with the first session that we begin on is on code development strategies, where we will have 3 speakers, and each session will basically have a discussion round where there will be an option for participants to interact with speakers through Slack medium. And after each talk, as already instructed in the email, after each talk by the expert, we will have a window of 5 minutes for people to raise questions through, but only while raising their hands and basically unmuting themselves to actually ask questions. And the chair of each session will actually take care of that round of discussion, along with the fact that just after after each session, there will be a summary and discussion round where the chair will also take questions from participants who are actually giving questions from the Slack. I will now request Dipanjan, who is basically the chair for the first session on code development strategies, to take over and basically welcome our first speaker, Mr. Sanjay Vandekar, who is a senior director at CDAC. And I once again welcome all the participants who have joined via Zoom link and also are basically looking at this live stream on YouTube. Welcome one and all. Dipanjan, over to you.
Okay, thank you, Bhargav. And again, welcome everyone to this workshop. So in the first session, which is titled Code Development Strategies, we'll have 3 talks. We're privileged to have Dr. Sanjay Vandekar, Senior Director of CDAC Pune, with us in the first talk. Then followed by Pratik Sharma from ISC and Shravan Hansoge from TIFR. So just to give all of, since it's the first session, I'll just give some basic instructions of how these talks will follow. So we have 25 minutes for each talk with 20 minutes for the talk and 5 minutes at the end for question answers. I will give the speakers a warning at the 18th minute on Zoom chat when you reach the 18th minute. And for all the participants, I will leave the floor open. You can write your questions on the Slack, on the Zoom chat, as well as on the YouTube, whoever is streaming on the YouTube. And we will try our best to collect all questions which are relevant and address it within the given limitations of time. So then let us begin the first session of this workshop. And I will welcome Professor Sanjay Vandekar to just start his talk. So Bhargav, have you made him a co-host? So Dr. Sanjay, please share your screen and you can unmute yourself.
I've made Mr. Vandekar the host.
Okay.
So we can just wait for him to share the
I'm
screen.
just sharing the slides.
Yes.
We can very well see the slides, sir.
Yes, thank you.
So we'll just wait for a couple more minutes before we start because the original time is 9:30. We are a bit early.
We're a bit early.
Actually.
Okay. Bhargav, maybe we can just start. Go ahead and start.
Okay.
Because Dr. Sanjay is waiting for a long time.
Okay. So we can.
Are able to hear me properly?
Yes.
Yes.
Please go ahead.
So myself, Sanjay Vandekar. Actually, I'm heading the Hpc Technologies at CDAC Pune. I'm also handling the national supercomputing activities in CDAC and mainly the supercomputing infrastructure which are getting developed under this national supercomputing mission. So I'll be talking about emerging trends in Hpc technologies and also the programming environments which are coming up for the exascale Hpc systems. So first, I'll give a brief about CDAC. Most of you know about CDAC and as well as NSM. So CDAC is a national body for HPC for more than 30 years and which is involved in design, development and deployment of HPC technologies and the systems across the country. We give solutions, HPC solutions to the users as well as offer them facility management. We are involved in training, HPC training, as well as application developments in various domains. And we provide national supercomputing facilities to the users of the country. Under National Supercomputing Mission, which is a Government of India program, CDAC is building number of supercomputing systems of different sizes and scales with a total compute power to the tune of 30 to 40 petaflops. So this is a brief about National Supercomputing Mission. There are 4 pillars in this, mainly the infrastructure development, then development of supercomputing ecosystems and capabilities in the country, application developments and capacity building in terms of human resource. So in the supercomputing infrastructure development, we already have put 5 systems which are operational in the country and 9 more are expected soon. Even though these systems are actually put up under at various institutions, the facilities are available across the country. So 40% is reserved for the external users and 60% to the host institutions. So people are welcome to use these systems. And as and when the more and more systems are getting available, I think more compute power will be available. Currently, most of the systems are almost 90 to 100% utilized. We have already developed one 200 AI petaflop national facility at CDAC Pune, and which will be released soon to the users in the month of April sometime. Under ecosystem development, we are developing various technologies like HPC processors, server boards, interconnects, and software stacks. Application developments, there are various domain softwares which are coming up. Under training, we already developed around 4,000 manpower which are trained, including faculties. And this is going to multiply with the faculties that are getting trained in this shortly. And we are planning to have about 20,000 manpower at the end of program. So these are the systems which are available currently. One is at IIT BHU, IISER Pune, and JNCSR. All these 3 systems are about 650 teraflop with a peak compute power of 833 teraflop. 2 systems of 1.3 petaflop are available at IIT Kharagpur and IIT Kanpur. So these are the 2 systems which are just come up, which are at JNCSR and IIT Kanpur. Now let's look at how the HPC system looks like. In the HPC system, as you know, that is basically the parallel computing environment where multiple nodes are connected using a high-speed interconnect, which is called primary interconnect in this diagram. And compute nodes are of two types. One is CPU-only nodes, and other ones are accelerated nodes. In the accelerated nodes, one has GPUs, CPUs, as well as other kinds of accelerators like vector processing, FPGAs, and so on. Now, there is a high speed requirement in terms of storage. So there is a parallel file system which is getting connected again to these nodes, and nodes can access this parallel file system parallelly and with a very high speed. Now, users get connected to the system using login nodes through the networking gateways, and they schedule the jobs on the compute nodes. Now, these are certain indigenous technologies I already talked about, so we can just go through that quickly. One of them is Hpc System software stack. I'll go in more details about that. So there are three main components of Hpc System software stack. This stack is currently deployed by CDAC on all these NSM systems. So three main components are operating system, which is mainly Linux in this case, then middlewares, and Hpc programming tools. In the middleware, there are file systems, provisioning tools, resource management tools, then monitoring tools. Under Hpc programming tools, there are communication libraries, mainly message passing interface libraries, where basically the programs can communicate to each other across the nodes. Then development tools involves basically the compilers, debuggers, performance tools, and so on. In application libraries, mainly the MASH libraries, GNU scientific library, these are optimized libraries which are available. Then visualization tools are available so that output of the program can be viewed very proper way as per the requirement. And there are various tools which are available, which some of them are domain specific also. Then performance monitoring tools, which are again there for basically checking out what kind of performance the system gives. So apart from the certain open source components which are optimized for this HPC systems, we have developed our own some certain tools which to complement this open source thing that is on the right hand side of the slide. Now let us look into the current trends in the technologies. Now we know that currently petaflop systems are available, and slowly we are moving towards exascale computing. So the 200 plus petaflop systems are available, and now recently 500 petaflop system by Fugaku, which is Japanese supercomputer, is developed. So now I think shortly we'll see the exascale computing. So we need to go through the current trends in this scenario. So I'll be talking about what are the trends in processors, memory technologies, HPC network, HPC storage, and programming environments. In the processors, we have seen that in the last 15 years, it was the x86 area where mostly Intel was dominating this HPC processor area. Other architectures like Power, Spark, and other vector processing, which were lacking the software ecosystem. But since last 2 years, we are seeing various general purpose processors apart from Intel and AMD x86 architecture, like ARM, Power. Again, these are from ARM is from Fujitsu is available, which is mainly the Fugaku supercomputer, which uses that. Then Marvell is having their own ARM architecture chips. Then Power is basically from IBM side. Now, what we are seeing is now in the current processors, the high number of cores are getting available day by day. Currently, 32 to 100 plus cores are available in single package. Another trend is there is a fast memory, which is the requirement as we are increasing the number of cores. So that is, again, we'll go into details in the next slide. Then vector processing is becoming a default standard in all the HPC processors. Unless you use vector processing power of the processor, you won't get the performance. Next one is on the accelerator side. Mainly the GPUs are dominating this world right now, which are coming from NVIDIA. But AMD is also getting into this. They already have the GPUs. Intel is coming up with their own GPUs. Under vector processing, NEC is having their own processor accelerators, which are actually connected on currently PCI add-on slot. In terms of data flow processing, FPGAs are becoming popular, and Xilinx and Intel are pushing those things. As I told you, now since the number of cores are increasing, the power dissipation in each chip is increasing. So currently about 200 to 250 watts processors are available, but that is increasing to 350 to 400 watts. So there is a cooling is becoming challenge. GPUs, the current compute power is about 7 to 15 double precision teraflops. And again, there also the performance in terms of thermal power requirement is going up. Now, this is a typical ideal processor which people are looking for, where different types of processor cores are being used for different types of requirements. Then, as the number of cores are increasing, bandwidths are increasing. So, byte per flop requirement is going up. So, people are trying to target 1:1 byte per flop performance using on-chip memory, which is called high bandwidth memory. This is linked with the fast network, which gets connected to the outside chips like accelerators and so on the coherent and non-coherent way. In terms of memory technologies, large and high bandwidth requirements are coming up. So CPUs are coming with 6 to 8 channels of DDR channels, basically. From DDR, technology also is increasing, changing from DDR4 to DDR5. As I told you, HBM is becoming de facto standard on chip, which is there in the current Fugaku supercomputer based on ARM chip. As the increasing of the large number of requirements in terms of size, NVRAM DIMMs are becoming popular, so to have the cost effectiveness. In terms of HPC network, high bandwidth requirements are going up as the CPU power is increasing, and low latency is becoming important for scalability. So currently 200 gigabit and less than 1 microsecond latencies are available. Then it is reaching to 400 gigabits per second in next 1 or 2 years. Topology is becoming very important for scalability requirements, and this topology depends on what kind of size of the network one need to have. In hexascale computing, you have hundreds of thousand nodes which are going to come up. So the topology is becoming important. So there are different topologies are getting available: fat tree, dragonfly, and multi-dimensional torus. Adaptive routing is becoming important, and QoS is becoming important as the networks are becoming larger and larger. In terms of HPC storage trends, as we know that not just simulation requirements are there. Now there are data analytics requirement, and deep learning and machine learning requirements are coming up, and that all that has to be addressed in a single machine. So there are 3 types of requirements, which is parallel file system, big data file system, as well as object stores, which are required, and various technologies are available, and including archival is one of the requirements. So hierarchical storage management is required as the data sizes are growing up. So there is a new file system which is being proposed and which is already available, called DOIS from Intel, which is again open source initiative, which caters to all these 3 requirements in a single file system, which is having high bandwidth and high IOPS. Now let us get into the details of parallel programming environments which are available. So what is the requirement of programming in a parallel computer? So application programmer needs to distribute data across the memories in the nodes, various nodes which are allocated to him, distribute the work to various processors which are allocated, and then organize and synchronize the work and data flow between these nodes. All this has to happen with least resources and most effective way for scaling and optimized performance. Now, so there are 2 types of models which are available. One is internode programming models and intranode programmers. As I told you, that compute node is having multiple cores and as well as accelerators as part of the node. So one need to have intra-node programming model for this purpose. And across the node, one need to have inter-node programming models. So MPI plus X is becoming a standard. MPI is mainly a message passing interface library. And there are more improvements are required in MPI for scalability and because of the hybrid nature of the architectures. PGAS is another model which is basically gives the global address space across the nodes. That also has the similar challenges. In terms of intra-node programming models, OpenMP is one of the de facto standard currently, which also supports now accelerators apart from CPU cores. Then OpenACC is a CPUs and NVIDIA GPUs is this is mainly used by NVIDIA GPUs. OpenCL is for heterogeneous node programming, including FPGAs. Now SQL is a new thing which is coming up, which is built on OpenCL concept. Cocos and Raja, these are new environments which are mainly C++ abstraction level programming languages, which actually use heterogeneous node programming, supports complex architectures with multi-level memories, has C++ APIs for expressing parallelism in your program. CUDA and HIP are mainly the proprietary environments from NVIDIA and AMDs. DPC++ is again Intel open source implementation of SQL. This is again open source available. People can start using this. UPC++ is again a PGAS based model. So as I've seen, now currently the left side of the node is available and we use MPI, OpenMP kind of programming models. The new exascale paradigm, there'll be multiple types of CPUs, then GPUs and accelerators. So one need to adopt this new programming intranode programming models to basically make use of this kind of architectures. This I think I already talked about that there is a combination of both HPC, big data analytics and AI ML. And so there is a requirement of multi-domain resource management and different requirements of storage and networking. So what are the exascale challenges we are facing now? So as I told you that there are accelerators, various types of accelerators. Now ease of programming is major challenge here, and availability of various open source and other applications on this architectures is a major challenge people are facing. In terms of network topologies engineering, as I already talked about, the data moment problem because there are large number of nodes, so there is a lot of time required to move data to and from CPU and memory as well as storage. And it also involves a lot of power when you move the data. So that is one of the major challenge. Then addressing all these three, HPC, data analytics and AI in a single system is again one more challenge because different environments are coming up. Parallelism is a major challenge because tens of thousands of nodes and millions of CPU cores are going to be there in this kind of systems. Then power is a major challenge. Reliability is another challenge because number of compounds in the systems are going up. Now, in terms of software challenges, in the programming models, the current models are basically low-level tools and which are not adequate to composing applications at high level of abstractions. So there is a need for a programming model which allows higher level of abstraction, as well as the different standard libraries and frameworks need to be developed so that this kind of large machine can be easily used. In terms of tools, there's the requirement of improved compilers, performance analysis, and other tools, which will make easier to develop high performance cores. Now, since the systems are becoming heterogeneous, there is a requirement to develop new algorithms which can actually match the available hardware and use optimally. As I told you earlier, that lesser data moment is one of the challenge. So algorithms need to be developed which can basically help in having less data moments, so which will allow us to scale and having lesser power consumption. Then as the machines are getting larger and larger, fault tolerant algorithms are major requirements, so that even if there are some faults in somewhere, the program should be able to recover and continue from that. Otherwise, rerunning the job will be a challenge again. In terms of debugging, there are different requirements. Now, currently, not just your debugging of the OS, the program, it has to be at OS and machine level also. Now, there is a requirement that people would like to start HPC programming. So we have come out with a small machine, which is, we call it Param Shavak, which is a ready-to-use supercomputer in a box solution, which gives about 3 to 17 teraflop of compute power. And it has a basically complete ready-to-use software stack, and its environment is same as larger HP systems. So we already deployed about 150 systems across the country. And there are three variants in this. One is HPC related, all the software stacks are available, including applications, open source applications. Then there's a DL based system, which is for deep learning applications, and other one is VR related application. Other than that, we have developed one 100 teraflop system. Again, this is for the next level of users. Again, this is a ready-to-use system with fully integrated software stack, and it has integrated data center with cooling and UPS. This system is available in 4 different architectures: Intel, IBM, AMD, and ARM architectures, and it has a ready-to-use open source applications. As I told you earlier, under National Supercomputing Mission, various training programs, workshops, hackathons are being conducted. So please look into a suitable program for your think at nsmindia.in. These are ongoing programs at various levels, starting from workshops to formal programs. As well as access to NSM system is available for scientists and researchers. So people can actually give the request. We can give the access to the users. Thank you very much.
Well, thank you, Dr. Sanjay, for this very wonderful talk, giving us the broad landscape of the present status of the computing architecture in India. And there are a lot of promises of interesting HPC technologies coming up, and hopefully will be used by the users. So I'll let the floor open to question answers. So what we'll do is we'll ask the participants to raise your hands if you want to ask a question right now. And if you are unable to raise your hands or attend Zoom, you can write your question on Slack on YouTube and we'll collect the questions. So if anybody has any questions, please raise your hand, go to the participants window and then raise your hand. So we're just, while we wait for some people to ask some questions. So Dr. Sanjay, this was a very fantastic talk. And what really I found surprising is there are a lot of already present HPC capabilities in India, which I think many users are not really aware of and how to use them. And there are a lot of new technologies also coming in where potential users can use this and run the different kinds of codes. I would maybe just briefly ask you, what kind of applications do you see being run and what kind of massively parallel codes are being run? For example, how many cores are the codes using, or how many flops are the standard softwares that use your systems that are using now?
Yeah, currently the people are using the system under various domains like bioinformatics, then material sciences, okay, and weather forecast, climate related research, and so on. Some of the astrophysics people also are using it. And then in terms of chemistry, physics, those kind of domains also they are using it. Now in terms of number of cores and other thing requirements, people are having different requirements starting from few hundred CPU cores to thousands of cores. So there are various requirements, but currently we have 3 to 4 systems only are available. So people are not able to run the larger jobs currently. because of the availability of things. There are a lot of queues available. So larger jobs will take longer time. So people are putting their jobs in the smaller number of nodes or some smaller number of cores, and then they execute that currently. But as and when the larger and larger systems are getting available, I think people will be able to run larger jobs also.
Right, thank you. So we have one question from Pankaj. I'll ask you, Pankaj, to unmute yourself and then ask your question.
Hi, thanks for a very nice talk. Can you hear me?
Yes, yes.
Okay. So I have a couple of questions, very generic ones. The thing is, like you just mentioned that larger jobs. So what do you mean by larger job? I mean, they require a lot more time or a lot more memory or something, or I mean, a combination of both, because of course, if you increase the CPU, I mean, core size, probably you can do it in a smaller size. I mean, it's a smaller time.
Yeah, larger job, I mean, basically, it requires larger number of nodes. Okay. Currently, we have about 150 to 300 nodes in a single system. Okay. So some of them are, let's say somebody wants to run 100 node job, then that becomes difficult because already the system is occupied. And then to run that kind of job, he has to wait for longer period. Okay. To get resources free.
So the second query is, okay, so what is the process to assess this system? Let's say, I mean, if one want to, perform some simulations.
Yes, so there is a actually form available from CDAC. The user has to fill that form and he gets the access to a particular system.
Okay.
Yes, so that is.
So it's just the form and I mean, okay, so slightly bit more. The form.
Pankaj, maybe we can leave the technical details for a offline discussion.
Okay, yeah, sure, no problem.
Yes, I think I can give the details once you, and then you can actually look for nsmindia.com in. Right now we are not put it because there are limited resources, but shortly we'll be putting up all the forms on that site.
Okay, thank you, Pankaj. We have one more question from Sharanya Sood, who's one of the organizers and can't raise his hand. So Sharanya, can you please unmute yourself and ask the question?
Yes, I am unmuted. So thanks, Sanjay, for a very nice talk. So I'm one of the users of your CDAC Pune National Forum Supercomputing facility for the last 3-4 years. So I just wanted to come to the point directly. So given the complexity of the numerical codes that are used by various scientists and also the kind of complexity of the systems that are coming in the future, and some of them are already here in terms of NSM. So will there be an opportunity to collaborate with people in the NSM data centers, so that, because we need to port our codes such that and make it updated so that, it scales and things like that. And sometimes these are beyond our knowledge of, code development and all. And this is where I think a synergistic approach towards, between us scientists and the scientists in the data center would help, who are experts in computer science and all these things. So I hope that there would be some thought be given in that direction.
Yes. So we already thought about it. There are two ways we handle this program of basically helping the users. One is basically we conduct hackathons where users come with their codes, and then there are experts who help them out in basically optimizing program. That is one way. Other way is we have a team actually which can help offline also for basically scaling your application, but may not be they may not be able to spend time in terms of actual coding, but they will be able to guide you definitely.
And Dr. Sanjay, we lost your audio.
Hello.
Yes,
yes,
we can
hear you.
Yes. So basically, there is a team available who can actually help the users, but they may not be able to code for you. Okay.
Yes.
So definitely, that team is already available. You can contact us, and we'll support you in that.
Okay. Thank you.
Okay, maybe we'll take one last question. Girish, I'll ask you to unmute yourself. You've raised your hand.
Yes, yeah, thank you for a very nice talk. It was very educational. I was just wondering that often in these talks, these numbers like 30, 40 petaflops are quoted. But as an astrophysicist, one of the challenges that we have is our codes are usually memory limited. I mean, Sharanya alluded to this, that usually the requirement is of very large number of nodes. We routinely already use above 1,000 nodes on various facilities for our simulations. So essentially, the number of interest for astrophysicists becomes the degree of fragmentation in those 30 or 40 petaflops. How big are the individual systems? So is there any thought given to this in terms of the growth of the supercomputing facilities in the next 5 to 10 years?
One bigger facility which is coming up here is our 20 petaflop system, single facility. Shortly, maybe I think another 2 years down the line, we'll have that. So which will have a larger number of nodes, as well as the memory per node also will be about 1 terabytes of memory. So whether that will help, I don't know. But there is another program which we are proposing for later stage, that exascale program. Once this current mission is over, that will be proposed. So I hope that with this we'll be able to support this astrophysics community.
Well, thanks, Girish, for the question. And I'll just take my privileges as host to ask one final question before I hand over to Pratik. So we are all very interested about the upcoming, infrastructure in India, because many of us have used heavily the supercomputing facilities abroad as well before coming here. And there, for example, my typical requirements would have been running codes on several thousand cores, structures like this, and I'm sure many have. So I hope that with the NSM coming up, we will get towards having some sort of facilities or usage possibilities in that direction. My question to you was, especially in Europe and others now, and the exascale era, people are going towards a hybrid model, so CPU, GPU. And the system administrators are sort of insisting that we sort of update our softwares to gear towards the direction. So is there any advisory from the supercomputer Hpc panel now, at least so that the code developers also can update themselves in that regard?
That's what I shown the various programming models which are coming up. So which can use this hybrid model where GPUs and CPUs are being used. So in one of the slide, I explained about various intra-node models which are coming up. So that I think one need to go through that and learn those new models, so that program can utilize these GPUs without modifying for a specific GPU. Okay, so that is basically useful for across the GPUs or across the various kinds of accelerator which are going to be available. So I think going towards these models is very important to use these hybrid machines.
And can you give us a brief timescale of when this would be? Because from our code development point of view, then we'll also have to invest some time to gear up for that.
So these are already available. Some of them are already available. And then people should start using them. Like I should use SQL, then there is a DPC++ is another model which is available. Okay. Then this Cocos and Raja, these are another models which are available. All these are open source models, and they are also gearing up so that they can support more and more types of GPUs and other things. Because everybody is facing this challenge. If let's say somebody wants to use NVIDIA GPUs, then he cannot learn CUDA separately. So high-level models will actually help them, so that new GPUs are coming up, new accelerators are coming up, your program is not going to change.
Okay.
So it is very important that these new models has to be adopted so that one can scale their applications.
Well, thank you, Dr. Sanjay, for this very wonderful overview. And I'm sure it was very insightful, at least for me and many of the participants here. So we will have, again, a short discussion where we can pick up some of the points discussed here at the end of the session. So I'd like to thank Sanjay once again for this nice talk, and then move on to the next speaker.
Thank you. Thank you very much.
So next talk is by Pratik Sharma from ISC, and Pratik will give us an overview about the idealized simulations of multi-phase circumgalactic medium. So Pratik, are you a co-host? Bhargav, can you make Pratik a co-host, and Pratik, can you then share your screen? Pratik, can you hear us?
Yes, I can hear you. I can't share my video.
Yes. So Bhargav, can you make, Bhargav, if you're online, can you make Pratik, okay. So
you are the
I'm the host now?
Yes.
Okay, Pratik,
Okay,
you are the host now, you can share your screen.
Okay, I'll share my screen. Okay, thanks a lot to Dipanjan, Bhargav, Sharanya, and all the other organizers for arranging this session. I think it's high time we talk about these issues. And I also thank Dr. Sanjay for giving a very nice overview of the infrastructure that is available now and in foreseeable future. So I'm actually going to talk more on applications, and my application will be circumgalactic medium. Oops. Okay, I'm sure everyone knows this, but computation is playing a bigger and bigger role in science today. So the classical division of science has been experiments and theory, but computation, modeling, machine learning, all these computational tools are bridging the gap between experiment and theory. And of course, in astronomy, we don't really have a lot of controlled experiments. So experiments are replaced by observations. But even there, a lot of modeling and quick analysis and all this is playing increasingly important role. Like with big telescopes generating huge amount of data every day, we need efficient way of analyzing the data on the fly so that we can follow up with these telescopes if there's something interesting. So computation is there very much present in almost at the back of almost everything that we do right now, but it will become even more important with time because computers are becoming fast and big. In astrophysics, computation is very, very important because the systems that we are interested in are highly nonlinear with a great number of degrees of freedom. I mean, it's very rare to have analytic solutions for such systems. They are highly chaotic, nonlinear, turbulent, and there are a lot of mathematical approximations involved. For example, instead of particles, you deal with hydrodynamics and so on. And you have approximate solutions to approximate equations. And I saw the title of the talks, and I think Jasjeet is going to talk a little bit about this. Now, this is a highly biased approach that I have for computation. So for me, it's a wholesome thing. I don't really look at computation separately because I consider myself as more of an applications person. So I choose the right problem. You must have an audience for such a problem. It should not be too hard to be unsolvable. And you should have some unique strengths to be able to solve the problem. We have to, and when you're a user of algorithms and computational facilities, you should know the algorithms, what the codes that you're using are built upon. It helps you a lot. You should write short programs and have a good feel for the problem, okay? If the problem is too time consuming, write it in C and Fortran and see if the execution can be made faster. You go for parallelization, MPI, OpenMP, using OpenMP, MPI paradigms, using whatever is appropriate for the system that you have access to. Of course, you should do scaling runs, weak scaling, strong scaling. So all these are, all these technical tools are extremely important, and they're extremely important for making use of the resources that Dr. Sanjay mentioned about in his first talk. And my approach is to use publicly available codes. For example, I use Pluto. In past, I have used Zeus. My collaborators have used Flash and so on. But you do not use them as black boxes. You understand them and you add to them what's needed. Okay, so this saves you the effort of writing a nice usable code. But if you know it well, you can add the functionalities that you want. And the code developers are very, very happy if you collaborate with on this. And I've actually done that in past. And all codes have strengths and weaknesses. So know what are the available options. So these are more like good practices in computational astrophysics. The debugging runs must run fast. You cannot wait for 2 months for your debugging run to give you an answer. Debugging runs should run on much less than an hour. In fact, preferably in 5 minutes, so that you can tune it, correct it very, very quickly. So there is a short turnover time for getting to the right setup. And just going to the high resolution won't solve the numerical problem. Some people who are beginners think that, oh, if I increase the resolution, all my numerical instabilities will go away. They won't. This is just wishful thinking, and it will just increase the time that it takes for you to solve the problem. Do not immediately trust the results. There are many ways for you to go wrong. It cannot be overemphasized the importance of testing. So that's why I've written it 3 times: test, test, and test. Diagnostics are very important. Things like volume average quantities, probability distribution functions, 2D snapshots, 3D snapshots, 3D movies, and observables. For example, column densities, if you're trying to compare with absorption spectra of quasars, for example. Now, right, so there's a lot of technical stuff that you will need to learn and have a good feel for, and that's very, very important. You cannot use HPC as a black box. As Dr. Sanjay was mentioning, with the newer and newer platforms require the user to know a little bit more about the architecture, about the programming environment, and so on. And after you've done all this, you should tweak your setup and have a best possible setup so that you can have a convincing answer, so that if you run all these expensive simulations, people believe what you're saying. And once you have a nice setup, it's very important to choose one fiducial run and then other runs around it, so that you can actually get a feel for the parameter space. And many runs are actually needed to build intuition. So this is sort of like what I follow and what I ask my students to follow. And again, to reiterate, just using biggest computer and the most sophisticated software is not an end in itself, right? You want to solve science problems. So you should not be like a hammer for which everything is a nail, right? You have to choose your tools to address the science problem. And that sort of is the approach that I take. And of course, I don't mean to sort of undermine the importance of computing facilities available. They are very, very important. But you have to use them, in this big picture. Okay, so here is actually a sort of a quick overview of cosmological galaxy formation simulations. So these are sort of the popular galaxy formation simulations around. You have on the left column, you have dark matter only simulations. And on the right, these have dark matter and baryons, gas and stars and feedback. So the right column is very complex. The left column is relatively less complex, but still very, very complicated and non-linear. So these are zoom in simulations. The top row is zoom in simulations. The bottom is large volume cosmological simulations. And these are like very, very popular simulations some of you may have heard of. Now, this has dominated the field of galaxy formation for a long time. And these simulations have extremely detailed physics, especially the ones on the right column. You have put feedback from stars, from AGN, magnetic fields, cosmic rays, conduction, you name it. So these are extremely complex. And all of them have a different take on what they are trying to address in cosmological galaxy formation. Even on these Zoom cosmological simulations, the resolution that you can achieve is up to 100 parsec. Okay, and now the question, so what I do are called idealized simulations. And why do we need idealized simulations when you have all these beautiful simulations here? And the answer is that we want to focus on the most important physics underlying all this. So, right, that's what physics approach is, that you strip down the problem into its bare basics and try to learn things deeper. Now, this is the problem that I'm motivated. This is the science question. As I said, for me, the science question is very, very important. So you should know the context in which your simulation work applies. So this is the circumgalactic medium. Image on the left shows a famous starburst galaxy M82. It's a multi-wavelength image. It shows the disk of stars in this galaxy in this green. In red, you see dust emission. And in this blue, you see X-ray emitting hot gas, which is a 10 to the 7 Kelvin, 10 to the 6, 10 to the 7 Kelvin. So this is a galactic outflow, a multi-phase galactic outflow. So we want to understand how this works. The image on the right is from the center of Perseus cluster. This is also a composite image with the blue in X-rays, blue showing X-rays. These filamentary red things are optical, and these sort of bubbles are showing radio. So what you see is that this circumgalactic medium, this medium around the galaxy, is extremely multi-phase. You have gas at temperature of 10 to the 7 Kelvin, gas tracing 10 to the 4 Kelvin, and even molecular gas and dust in some of these. So the question is, the key question of this field is, how does cold gas originate and how does it survive in such a harsh environment with hot gas, which is trying to evaporate it? Now, these are some of the examples of idealized simulations of circumgalactic medium that my group has engaged in. So I'll not be talking about all of these, but I encourage you to have a look at it. And I promise you that these are as interesting as cosmological simulations that you have seen and enjoyed. So, so I will actually focus mostly on the first problem listed here, but other people in my group have focused on turbulence in the intracluster medium, feedback AGN jets in the intracluster medium, galactic outflows of the kind shown here in M82, and thermal instability and its implications for the ICM and CGM in general. Now, you'll notice that, you know, the key physics in all of that is called cooling, you know, is basically radiative cooling. And what goes behind in almost all these setups that I talked about, and in all cosmological galaxy formation simulations, is radiative cooling. So, and that is actually approximated by something called a cooling function, which is shown here. Lambda as a function of temperature. This is a log-log plot. So this is high temperatures. Here at 10 to the 7 Kelvin, all the ions are fully ionized and the plasma radiates via free emission or Bremsstrahlung. At lower temperatures, higher ions like iron and oxygen are not fully ionized, and there are line transitions which make them efficient coolants. At even lower temperatures, almost everything becomes neutral, even hydrogen recombines, and the radiative efficiency of the gas goes down, right? So this physics of this atomic physics plays a very fundamental role in galaxy formation. If you're sort of listening, you know, if you're hearing this for the first time, this would appear surprising, but basic physics has a very far, you know, has far-reaching consequences. Okay, so this is the cooling function. It just quantifies how radiatively, how efficiently a gas parcel cools given its temperature. So the gas at 10 to the 5, 10 to the 6 Kelvin cools really, really efficiently. Okay. Now I'll be talking about cloud crushing problem. So the cloud crushing problem is actually a model problem, an idealized setup, which tries to learn about this multi-phase gas, which is sort of being blown by this hot plasma running through it. Okay, so the problem is the following, to boil down to its bare bones, is that you have a cold, dense cloud and you have a headwind which is dilute, and this cloud is being pushed by the wind, right? There will be drag force between this wind and the cloud, and this cloud will be pushed. And there are certain dimensionless parameters of this problem, like the density contrast between the cloud and the wind, the Mach number of the wind relative to the velocity of the wind divided by the velocity, the sound speed in the wind, Mach number. And we can actually get some important time scales out of these dimensionless parameters, like the crossing time, which is just the time that this wind takes to cross RCL. RCL is the cloud radius, or the cloud crushing time. So this cloud crushing time, or TCC, is the time for that Kelvin-Helmholtz instability that will take place between this wind and cloud because of large shear will mix this cloud into the wind. So this is the cloud crushing time. The drag time is another dimensionless time scale, not dimensionless, sorry, another time scale, which sort of quantifies how quickly this cloud will gain momentum from the wind and become co-moving with the wind. So eventually this cloud and this wind will start moving together. And that is what we want. And that is what the observations of the galactic outflows show. Now, if you look at these time scales, the drag time scale is chi times t cross, and the cloud crushing time scale is chi to the 1/2, and chi is of order 100. So basically what it means is that the cloud will be mixed by Kelvin-Helmholtz instabilities before it can be pushed by the wind. So this actually is a puzzle. How do these galactic outflows have these multi-phase gas moving out so fast, rather than being destroyed as this naive criterion would suggest? And this is the context of the cloud crushing problem with radiative cooling. So it turns out that radiative cooling plays a very important role in cloud growth and this momentum transport between the wind and the cloud. So these are some results from some simulations done by my PhD students Vijit and Alankar. And what it shows is the mass in the dense cloud as a function of time normalized to the cloud crushing time. And what you should take away is that these dotted lines show situation when there is no radiative cooling. And what it means is that in absence of radiative cooling, all clouds get mixed by a few cloud crushing times. Okay, but when we have radiative cooling, and the radiative cooling becomes more and more important for a larger cloud size, then you can have a qualitatively different behavior, which is shown here for the blue and orange line, that clouds actually get destroyed for a little bit, but they can grow and grow enormously after some time. So this is actually a very interesting physics that has implications for galactic outflows. And this is from the same simulations. We are plotting the velocity difference between the cloud material and the wind material normalized to the initial wind material as a function of time, and it is normalized to the drag time scale that I mentioned. And these are the same simulations results that I showed in previously. Here there is a fundamental difference in terms of the mass transport between the two phases, but the momentum transport is more or less the same. The wind and cloud become co-moving at about the drag time. Okay, so this is also very interesting, because what it means is that once you are in the cloud growth regime, they will also gain momentum on a short enough time scale and may explain observations. Here is actually a movie from these cloud crushing simulations. These are very high resolution simulations. Oops. So I'll play it again. Oops, just a sec. Let me try to stop it. Okay, so there was a cloud initially, and now there's a headwind. This is hydrodynamics with radiative cooling. So this cloud gets crushed because of Kelvin-Helmholtz instabilities, and you can actually see these tails and wakes. This is using a Pluto hydrodynamics code, which is a publicly available code. The people here, the organizers are developers, in fact, of part of the development team of Pluto, so this is a publicly available code. Our group uses it. This simulation was run using up to 16,000 processor cores on Sahasra at SERC. And you can actually see this is a density snapshot. You have dense material getting sort of stripped and reduced. So this cloud moves out of the computational box, but the tail still remains. And what you will see at later times is very, very interesting. See, now this mixed gas, which has intermediate densities, is starting to cool in the wake. And this is very, very interesting. You can see that the wake becomes massive and dense. And this is what was responsible for those growth seen at late times. You can actually see this tail reforming, even if the original cloud has left. And the physics here is that this shear between the wind and the cloud creates intermediate temperature gas, which has a very short cooling time. Okay, and this is like a volume rendering snapshots of a given snapshot. You are looking at the cooling time surfaces, and you can actually see that this wake of this gas, of this multi-phase gas, is extremely complex. And the color shows cooling time, and this is a surface. This is a surface of a constant density. It's an isosurface, and this is the transparency. So the gas, which is very hot, you can see through it. So this is the importance of visualization. You can really get a very good feel for the system that you're studying. So it's worth investing effort and time in being able to do parallel visualization. And Vijit and Alankar have done a very good job at this. Okay. Now there's a lot of physics, and what I'm going, I have about 5 minutes, I think. So this problem has been studied for at least 25 years. So why is it that we chose to run it? As I mentioned, you have to choose your scientific problem very carefully. And the reason we chose to study this problem is the following. There was a very important paper in 2018, which actually clarified that if this size of this cloud is big compared to a certain threshold, then you can have growth. And this threshold just corresponds to the physics of this cooling time of the mixed gas compared to this cloud crushing time. And you can actually write this criterion in terms of the radius of this cloud. So basically what it means is that for typical parameters, if your cloud is bigger than 2 parsec, then that cloud will grow because of radiative cooling of the mixed gas. Okay. Now there were other papers following up in this one, and they found that this threshold, they did their simulation, they found that it's actually factor of 10 bigger and has very different scaling compared to chi. So this was an example of a very important problem where there was a big puzzle. So that's why we thought, even though it has been studied by like at least tens of groups, we'll study it again because we want to resolve this discrepancy. And that's what we tried to do. In fact, this is actually a plot of these triangles and circles are simulations from the follow-up paper, and these triangles and circles in color are our simulations. So what we find is actually we find growth of clouds even for clouds which are smaller than this Lie criterion, smaller than this. And so you can actually see these triangles fill in this space below this dash line. That means my clouds can grow here, which is inconsistent with the 2020 paper. So what we sort of tried to do is we really designed careful simulations so that we can fill in this gap. So these colored lines are predictions from the Gronke-O theory, and this dash line is prediction from the other theory. And you can actually see we did these simulations where we do see growth for clouds which are smaller than this. So we were able to resolve this important puzzle. So I'm actually not going to go through all this, but so there was a lot of follow-up papers. In fact, there was a paper just before our paper which said that we find that the hot gas cooling time rather than the mixed gas cooling time that sets the transition radius. So it was an important problem. In fact, and after we pointed this out that you should look carefully at how cloud grows, they also find results which are consistent with this. Now, I think I'm actually running out of time, but this was just an example of how a carefully designed simulation can do things for you. So these are my conclusions. I'll quickly sort of just mention important points. A lot of creativity is needed in using powerful tools of HPCs. So just don't think that, oh, I have the biggest computer cluster, I will be able to do the best problem. No, there is a lot of creativity involved in designing and coming up with the best setup. My other advice is don't reinvent the wheel. Use public resources, share know-how and data with broader community. That also helps you follow good practices in computational science. And there's a huge application for such idealized simulations, which I illustrated through this cloud crushing simulations. So, I hope this just gave you a flavor of non-cosmological galaxy formation simulation and how much we can learn from them. So with that, I'll actually stop. Thanks.
Well, thank you, Pratik, for this very wonderful overview from the user's perspective of one of the large-scale work. And I completely agree with you that we should not reinvent the wheel. And what is more important is good practices in computational science, because now that we are having access to large-scale resources, it's very important that we are, restrict ourselves to using it wisely, and not just because we have large number of cores, we use whatever we have. Mm-hmm. Now, I had several questions regarding your cloud crushing simulations, which are fantastic to look at, but I will just wait for others to have some questions. So
let me just play this movie while we address the questions.
Fantastic, and I have many technical questions. So there are many hands up as well. So first is Nishant. I'm unmuting you.
Hi, Pratik.
Yes.
Hi. This is Nishant. Yeah, thanks for a nice talk. I just had one question on something, this cloud crushing time you discussed.
Mm-hmm.
So I was just wondering, the cloud, unlike the solid objects, would also allow the interior solutions,
mm-hmm.
which I believe, for example, one example that I can come up with is this hill vortices. That might, if not totally suppress, would at least delay the Kelvin-Helmholtz instability, or things might slow down. In fact, I was just wondering if, depending on some parameter, or has there been any occasion, depending on the parameters, when you have seen the cloud being more stable compared to some other cases?
Right. This is actually an excellent question, Nishant. So, I mean, I am aware of certain global mode and a global analysis in the context of filaments by someone called Neer Mandelker,
mm-hmm.
and I'm sure there is stuff on this even in Kelvin-Helmholtz, because Kelvin-Helmholtz is as classic as it gets.
Yes.
But I have actually not paid attention to that. It was, for me, it was really this puzzle to resolve these two things, and it was really totally computational. Approach.
Yeah.
Mm-hmm. But
okay, so I'll maybe at some point I will discuss more. I'm also just wondering about the stability of some of these large blobs
mm-hmm.
that could perhaps be stabilized by simply having some interior solutions. But but maybe in simulations it may be worth perhaps looking at if there are some parameters in which there are some modes inside the cloud that could, whether they are
definitely the cloud will have its own sort of global oscillation modes. I totally agree with that.
Yeah.
Yes.
Thanks.
Thanks, Nishant. Next is Kinshuk. I'm asking you to unmute yourself.
Yeah, Pratik, wonderful talk. So, do you consider cooling by dust grains when you do these simulations for clouds?
This is an excellent question. So these simulations, these results from simulations appear as if they are real galaxies, but they are not, right?
Yes.
None of these simulations take the dust physics in any serious way. So, they will have, a lot of these simulations cut off cooling below 10 to the 4 Kelvin.
Yeah, in fact, if you just see this extinction by dust, it will be significantly more compared to anything else.
Mm-hmm. For what?
For this radiation, because they will also absorb.
Mm-hmm.
So
right.
basically, you will not have most of them will be taken away the dust, if I am not wrong.
Right. So one thing that I want to mention is that we are really talking about the CGM, which is not as dust. The circumgalactic medium is not as dusty as the interstellar medium. The densities in general are lower. Like, this cloud has a density of 0.1 particles per cc, this is the dense phase. The diffuse phase is even lower. So dust perhaps is not that important for the circumgalactic medium, but I agree, there is observation of dust in the diffuse phase as well. And dust is something we really don't understand a lot about, even in the ISM, forget about CGM and more exotic places.
No, this is a very valid question. Maybe just I'll use my privileges to chip in, because we see this kind of clouds being pushed out from the plane of the galaxy itself, and we see them in CO observations. And how do you form molecular clouds that are moving at high velocities? That is the challenge I think Pratik is trying to answer. And we are just at the rudimentary phase of it. We just, similar to Pratik, we can now only do atomic cooling. And including a lot more physics makes the problem so complicated that we often lose insight of the fluids. So I'm sure Pratik will be building this up in phases as
right, absolutely. So for example, the approach is to break it down so that you can have reliable models at every scale. You cannot have one simulation that solves cosmology and life on planets and nano structures. You have to break it down. That's what we do, right?
Well, thanks, Kinshuk. And maybe we can have more questions at the end of the session. So Abhishek is next, and this is the last question because we are late for the session. So Abhishek, I'm asking you to unmute yourself.
Yes, thank you. Hi, Pratik. It's a nice talk. So I have a very basic question. So basically, do you have any special information of these clouds, like how far are they from the galactic center?
Right. So these clouds are ubiquitous. These are just two examples seen in emission. So emissivity is higher in higher density. So these are close to the galactic disk. So this is like 20 kpc is the scale. So this cloud galactic outflow is of order 10 to 20 kiloparsecs. These are 40 kpc scale, multi-phase, dusty molecular gas filaments. But even beyond 100 kpc in galaxies like Milky Way, you see cooler phases in absorption.
Right. Yes.
But yeah. So it is ubiquitous. You have to explain it.
Right. So like if you do similar idealized simulation far away from the like galactic disk, for example, let's say 500 kiloparsec or so. So will you be able to see these kind of phenomena?
Right. So that's something that I haven't really talked about. That aspect is this. My feeling is that the gas which is very far away from the disk, from the central part, is happening because of thermal instability, and which is aided by large fluctuations from infalling structure, from filaments and so on. So this is something that I did not talk about, but I have actually spent a lot of time on this, that if you have hot gas, if the cooling time to the free fall time of that hot gas atmosphere is lower than a threshold, it has a tendency to condense out. And that perhaps explains a lot of far away multi-phase gas. It's difficult to throw out multi-phase outflows to hundreds of kpc.
Right. Right. Thank you. Thank you.
Well, thanks, Abhishek. Unfortunately, we can't take any further questions. So, Anindya, I see your hand up, but if you have a question, I'll ask you to write that question in the Slack channel for this session, and then we'll get back to it if we can at the end of the session. So thanks very once again for this very wonderful talk and the wonderful overview. So let's all thank Pratik and then move on to the next speaker, Shravan. So Shravan will tell us something about how to use machine learning in his work. So Shravan, on to you.
Yeah, sorry, Pratik, I'm going to stop your screen sharing if that's okay, and then show mine.
Yes, please go ahead.
Thank you so much, Dipanjan and the others organizers for inviting me to give this talk. Sorry, just a second. Yeah, there you go. So let me just begin right away and start telling you what I've been really interested in the past several years. So here's a nice movie of field emergence, as we call it. So new magnetic fields sort of emerging at the surface of the sun. This is a continuum data from the helioseismic and magnetic imager. It's a space-based instrument. And you can see these magnetic fields, a small cluster of magnetic fields. Oops, sorry, I can't move my mouse button over it. You see a small cluster of magnetic fields that, you know, a little active region, as we call it, that emerges. But what's actually interesting is something that follows it right now. And you'll see this with basically zero warning, this giant complex of magnetic fields starts to form right here. And so you can see it's a monster compared to the other one. The other one's almost vanished. And so this is the sort of really interesting problem that we try to understand. How do magnetic fields emerge? What is the fundamental physics that governs their emergence? Can we sort of say something about when these things will emerge? Because these magnetic fields affect space weather, which I'll describe in a second. So these magnetic fields, as I said, they appear at the photosphere of the sun, but they also make their way to upper layers into the chromosphere and into the corona. So you can see here that, you know, these are the sort of bipolar magnetic fields. The different colors indicate different polarities of the field. And so you see magnetic regions all over, and they're strongly correlated with the coronal emission signatures over here. So in other words, they sort of make their way to much higher layers, and then they impact the space environment of the you know, in the heliosphere by various complicated processes. So for instance, here you see a spectacular film of a violent ejection event. So you can see huge clouds of high energy particles are basically ejected from the surface. I show that again. What happens is you have these field lines that are, you know, lacing the entire chromosphere, upper atmosphere of the sun, and their foot points are in the photosphere, where they're sort of jiggled around by convection. And you know, over time, these the field configuration becomes increasingly complicated, and sometimes they become highly unstable, and then they explode. And so the question is, can we predict this? What is the physics of this, and can we sort of try to predict this? What's going on with the, you know, with the underlying physics there? And as I just said, you know, these solar flares have zero warning. Flux emergence has zero warning. New magnetic fields that emerge. You have these huge coronal mass ejections, which are extremely violent as well. They have a little bit of warning, but generally, you know, we don't know very much in terms of we don't have much headway in terms of what's going to happen when. And so very briefly, as a practical standpoint, I'm not as interested in the practical aspects. I'm more interested in the physics of what we can do. But very briefly, this sort of tells you how it's impacting us. And it's impacting us in a variety of different ways, especially contemporary society, because we depend so much on telecommunications, you know, sophisticated electronics, satellites, and so on. So it's quite important as we move into the future to try to understand and predict solar magnetism from a practical standpoint. There's a huge number of instruments that looks at the sun, constantly being launched, and some are decommissioned, of course. And so you can see that various aspects, none of them are directly, of course, looking at the sun. Some of them are measuring the, you know, the solar wind and various aspects of the magnetosphere, Van Allen probes, for instance. So there's a tremendous amount of data here, and you know, presumably you can do something with the data that are not, you know, things that are not directly possible with conventional methods of physics that we typically use. And so that's the goal of my talk, is to try to explain how you can bring to bear machine learning to discover new things, to do new physics, basically. So here, let me describe. Take a minute to explain the philosophy of this. So firstly, you know, we have, as I said, tremendous amounts of data. So terabytes from, you know, all different instruments and so on. And the idea is basically that you can train a machine using these magnetic field features, or using features that we know from, you know, we know to be correlated with flare events or coronal mass, or whatever event. So you know that, you know, from a physics standpoint, you know that, you know, some phenomenon A creates some is causally linked to something B, some event B. And so you want to find, we know it, we feel it, you know, we have a certain sense for it, but not necessarily evidence, and not necessarily understanding what that causal chain is. And so that's the first thing. How do you connect seemingly disparate things, right? So I have an image, let's say, of the sun, and I want to be able to predict the solar wind an image of the corona, let's say, and I want to be able to predict the solar wind for 5 days from now. Can I use these two? Are these two correlated? How do I even build a correlation matrix between these, between these phenomena, or rather between these measurements? And so, philosophically speaking, a lot of people do very sophisticated numerical simulations. In fact, this is what this whole session is about. But there are problems with that approach too. One, a lot of most numerical simulations, I mean, let's just admit it, don't really address the right parameter regime, or simply can't afford to take into account all the relevant physics that are important for simulating something. Of course, I mean, not to say that all simulations are false, or somehow that's not at all my point, but rather that they miss various aspects of the underlying physics, simply because the dynamical range of the parameters is so large. In that sense, machine learning fills a very important gap. So with a machine, if you have good data, I mean, of course, this all hinges on being able to have high quality data and lots of it. If you have lots of data, in principle, you don't have to bias the system with some physics, or rather a numerical calculation or certain assumptions, right? You say, well, you throw the data at the machine. It's very difficult to do it. It's not easy. So I'm just speaking lightly in some sense. But if you throw the data at the machine and you ask the machine to build a model of correlations, then in principle, it's an unprejudiced in some sense. Of course, you can always, it's very sensitive, so very easy to prejudice it. But in some sense, it's unprejudiced models of phenomena, and without adding in prior physics, without polluting this with too many assumptions. In principle, it should be possible to extract new physics. And so that was the approach, or that was the philosophy that we had in the group several years ago. And so we've been sort of gradually building towards it. But as you'll see in my presentation, it has mixed results, and I'll describe why that is the case. Okay, so that's the general philosophy with which we've approached this. And so we say, let's say I have an image of that sunspot, and then I know that it flares. And then I ask, okay, they train this machine with this picture of a sunspot, and I say, okay, can you tell me if it's going to flare or not, and when it will do so? So you can do a lot of interesting things like flare prediction. Sorry, this is this is prediction of active regions. This should also be flare prediction, and for active region emergence, I just showed you how these, this first cluster of fields emerged with a little warning. And then the monster of a sunspot group came, days later with basically no warning again. And the question is, which one becomes big, which one will dissipate? Again, that's all not clear at all from just looking at this. It's simply not. We can't really say what's going to happen to these active regions. So this is the thing that this whole effort is rests on. It's being able to interpret the machine. So one last thing. Philosophically, again, most people think of machine learning, and rightfully so, as a utilitarian. Well, I want to be able to classify something. I don't want to be able to think about it, and the machine is very powerful at doing it because it's able to do graphics recognition and computer vision extremely well. So that's what the machine is doing for me, and that's great. And of course, it works extremely well if you train it well, and so on. But what we're trying to do here is not so much use it as a tool to, predict something, predict space weather, predict emergence. We're not trying to create a pipeline to sort of, as a forecasting. I mean, eventually, I suppose that's a very practical, utility of this tool. But right now, what we want to use it as a physics, as a black box, which has understood some physics, which has understood some correlation in the data. And we try to unpack the box and try to see, well, what is it understood? Very, very difficult, actually, machine interpretation. It's an entire field in itself. So I'll describe briefly. So there are two problems that I want to describe. We're working on many different simultaneous problems in this. But there are two cases that I want to describe as a case study. The first one is precursors to solar flares, and the second is a little bit of work that we did on the origin of solar wind, again with mixed results, but it's an interesting analysis. Okay, so what are flares, right? Flares basically, as I said, are these field lines, they typically come from large flares come from large magnetic regions. We know this empirically just from looking at a lot of these flares. And so, the amount of X-ray flux that comes from it is what's important in judging whether it's going to be a threat or it's a harmless feature. And so there are these two types of flares called M and X, which produce a fairly large X-ray flux. And it's, these statistics of these occurrences of these flares is logarithmic, and as the amplitude of these, the X-ray flux increases, the frequency also decreases correspondingly. And so these X ones are the ones that we need to be aware. Beware. So it can really have a profound effect on satellites and create some damage at any rate. And right now, the most sophisticated techniques are this NOAA, which is the national something in the US it's for space weather prediction. I'm sorry, I don't know what. Oceanographic something. Anyway, NOAA predicts. It's an institute that predicts. It tells you, whether the sunspot is likely to flare, whether it's, what's going on, what are the physics of this sunspot, or how is it going to behave rather. And what it needs is is an expert understanding of sunspot morphology. Someone's looked at like 100,000 sunspots and built in their brains a very sophisticated correlation model. And it does reasonably well, actually. So they typically look at, there are these people who are experts in this, they look at it and they say, well, this is likely to flare, or this one we can ignore. With some degree of probability, it appears to succeed. But, one of the holy grails is, can we say something in a time dynamics and in a dynamic sense, and is this going to flare in the next 24 hours? Can we say something about what's going to happen? What feature will appear as a precursor to it. And these precursors they're a bit of a holy grail. But I'm not saying we found a precursor, but let me explain to you what we've tried. So these are the data from the helioseismic and magnetic imager. They have an automated algorithm. These are different sunspots over here. This is a sunspots and active regions and so on. They have a segmenting tool, which says, okay, well, here's a little active region. Active region is another way that we call a magnetic region. And it segments them. It says here, it puts bounding boxes around them. And it says, okay, this is and it identifies some sort of centroid of these regions. And so very nice data. So they have a nice little algorithm that gives us these regions and says these active regions are now visible on the sun. I've segmented them for you, and here they are. Sorry. And from these, you generate, very sort of coarse scale features. So you can say, well, here's the various averages of this, right? Here's the total average unsigned flux. Here's the area of this region. We know that the bigger the active region is, the more likely it is to flare and flare, big flare, right? So X5, XX class or M class and things like that. Well, what is the total free energy of this? What is the free energy also is an indicator of how much energy it has to expend on a flare. And net current per all of these features, which are, I don't need to define them, but sort of the arithmetic definitions are here. You can compute these quantities from these, you need vector magnetograms, and that's what the helioseismic and magnetic imager gives us. It gives us vector data, so the radial and the longitudinal and latitudinal fields. And so from these three components, you can compute all of these quantities. And typically we find that they're strongly correlated in some sense to the flare activity. And one of the questions that we asked is, can we say something about how these features evolved before and after the flare? So there's lots of these parameters, there's about 25 of them. And we try to understand, well, it's a high dimensional problem. So can we sort of break it down and understand the physics of this? So this was a first case that we tried. We've now graduated to doing more complicated things. But this in itself was very productive in some ways. We use this machine known as a support vector machine. It's a very simple, it's a linear machine really. It builds a hyperplane, if you will. So you have all of these red dots and blue dots, and you ask, what is the best fit separator between these? So the equivalent here is what sunspots will create an M class or X class flare, and what sunspots will just harmlessly, rotate across the face of the sun, right? That's the question that we want to know. Which of these is a flaring? Flaring is, weak flares are irrelevant to us. So which of these is, when I say flaring, it means strong flares, M or X, and which of them is non-flaring? And so this question says, all the sample of sunspots, and I have to build a hypersurface. It's a complicated surface through this region, and it demarcates the boundary between these. And so we train the support vector machine. The input is all of these 25 parameters for each active region, and the output is is a binary classification. Is this going to be a flaring, or is this a non-flaring active region? Now, the thing to keep in mind here is that so it's a time series, right? So I can actually predict what's going to happen as a function of time. And then, the other important thing is that most active regions don't really flare big. I mean, they have tiny flares, and they just sort of, don't really affect us in any way. So it is a classic problem in machine learning called class imbalance, where you have 10 times as many non-flaring. We have 10 times as many of these as we have these. So this presents, again, another challenge, because if your machine just simply said everything was non-flaring, you would be right most of the time. 90% of the time you'd be correct. And so you could just go and say, well, I have a machine that's 90% accurate, and you'd probably be right in that definition. So you have to take a lot of care to define the right metrics, to oversample the data. These are non-trivial challenges in preparing training the machine. So one remarkable thing that we found was that, so you train all of these data, and then you keep a segment of the data that you call unseen or test data. And then you say, well, how does this machine do on that unseen data? So it has not seen those active regions or magnetic regions prior to this. So it does very well. It tells you these are the true positives, which means that it's a correct classification of flaring active regions. It says that nearly 80% of the time, so let me tell you what the axes are. Machine output is the probability that this will flare. So, 0.9 is with high probability, and 0 is, low probability. This time equal to 0 is, it marks the flare time. So we have, as I said, hundreds of flares, not too many actually. There's not that many M and X. I told you the frequency is not that high. So we sort of aligned them. We have time series of all of them. We aligned them so that at time t equal to 0 is when the flare occurrence happens. And this is the pre-flare, this is the post-flare. And then you can see that days prior and days after, the machine seems to suggest that this magnetic region is ready. It's in a waiting state. It's waiting to flare, and it's an unstable configuration even after the flare. And so that's a very interesting thing. This is not something that we had anticipated before. And so the error bars are tiny here because this is a statistical result. So you have to keep in mind that if you looked at any given flare, we won't get such good statistics. You're not going to be able to produce such tight error bars. It's just because we had hundreds of flares and we were able to analyze all of them together that we get some really nice error bars here. And one new physical thing that we discovered that hadn't been understood before is that there's this quantity called net current helicity, which is a quantity that determines it's the current. It's basically the electric current in that active region, and it's prior to the flare, which is t equal to 0. This is pre-flare. This is post-flare. This is that quantity ABS NJZH, which is the absolute net current helicity. And it rises very sharply, peaks at flare time, and then sort of gives way. So it's almost like it's releasing its current. Again, this is new physics that we hadn't appreciated before. Sorry, you can ignore all of these things. These other quantities, they're not relevant for this discussion. So yeah, so this peak is very interesting, and it tells you that this is something you need to watch out for when something is likely to flare, that its net current helicity will continuously increase. And so now we start to ask more complicated things. These are, remember that what I said was these were very coarse features. They're averaged over the entire active region. But now we start to look at more details, right? We say, well, what's happening to the dynamics of the magnetic region? Here is HMI time series of HMI data. This is AIA, which is an atmospheric imager, again on the same satellite. So every time, so if I move the mouse button, Okay, I'll just explain. What's happening here is this is a time, of course, time is proceeding. You can see all of these things are evolving. And when it jumps to, this is the machine. This is the machine prediction. This is 1, it says 1, and it's either 1 or 0. That's the thing. And then you can see that the machine flips to 1 here. These black lines demarcate exact flare locations. So prior to the flare, some distance prior, I mean, there are some little blips here, of course. It suddenly switches to 1 and switches back to 0. There's some errors in the machine for sure. And, again, there's a little error here, but then it switches to 1 and stays at 1 for a while, and 3 flares continuously happen, 1, 2, 3. And then it flips back to non-flaring when another flare happens. As I said, there are errors in the machine, so it's not perfect. So I want you to look at this red thing here, and you can see what happens, not now. Now there's a little error. You can see some little fluxes emerging, some little black stuff is emerging right there. And then now you can see a huge, not huge, but whatever, a notable amount of flux has emerged. And so this is the opposite polarity flux, right? So it increases the sort of the gradient of the magnetic field. And so this whole region, the machine has recognized as unstable. And so then, right then the machine says, well, this thing is now starting to look like it's likely to flare. So this is the kind of thing that you could really do, right? Now, this is a simple machine. You could start doing even more complicated things. You can do time series video recognition and stuff like that. So we haven't really done all of that stuff quite yet. But it already tells you that this flux emergence event, this little flux emergence event, has likely tripped the system to an unstable state where it's likely to explode multiple times. Okay, so that's sort of the flare thing. I just want to say that we've been working on it a bit, subsequently as well. The problem with the flare analysis is that there simply just aren't that many solar flares of notable magnitude. So we, wouldn't say abandoned it, but we sort of put it on the back burner for now. Another interesting problem that we worked on is the origin of solar wind. So here's a little movie that I got from NASA's website, and a colleague of mine sent me this. So you see the sun is here. This little dot here, whatever thing here is the Earth. And this is from a coronal mass ejection. So there's this huge blast of high energy particles that's just been simulated. This is simulation. It's been released from the sun, and you can see them being deflected by Earth's magnetic field, of course. So they're sort of propagating around Earth. So the question is, this is not really exactly solar wind, but even under quiet circumstances without a CME, of course, solar wind particles are being deflected by Earth's magnetic field, and so can you predict these wind properties, right? Can we say something about the solar wind? Because they're all born in the sun, they originate somewhere in the sun. We don't exactly know where or how. And can we say something about the wind properties? Again, you can use this as a prediction tool, of course, later, but we approach this not from the prediction context, but from successful prediction will mean that the machine has learned something. And so that's the context from which we approached it. So there are two types of solar wind. There's a fast wind, which moves really fast, 600 kilometers per second. And so it traverses the distance from the sun to Earth in 2 or 3 days. And then there's a slow wind, which is around 250 kilometers per second, and it takes a little longer. And so the question that we asked is, can we use coronal images of the sun taken by these two, in these two band passes by this instrument called the Atmospheric Imaging Assembly. It's a space-based instrument. And so this is looking at the sun in these two band passes, and it says, okay, I feed in, this is the input image of the sun, that's the input. And then the output is the coronal wind speed, is the solar wind speed that we measure at L1. So there's a satellite at L1 that captures the wind speeds. And so can we measure these things? And so it turns out that, and then you use something called, what's that called? Sorry, I forget, there's a grad cam, that's right, sorry. There's something called a grad cam that tells you where the sensitivity of the machine is. It tells you what the machine is looking at in an image, in a given image. It says, well, the machine is looking at this and that. So there are two types of features. This has been theorized a while ago, but evidence is, there has been some evidence, but this type of evidence is very clean. So there are two types of features that are thought to drive the wind. There's coronal holes and active regions. So active regions, you know, coronal holes are these, they're also features of the sun. And so there's sort of these big holes in the corona basically. And it's thought that fast wind basically originates from these. Some fast wind also from active regions, but the coronal holes are a dominant source of them. Similarly, the slow wind is thought to come from active regions. And so we noticed when we were training this machine, we trained the machine and it worked. It didn't work as well as we wanted, but it worked. And then we said, well, what is the machine looking at in these images? And it says that, 3 days prior to a fast wind event, if you will, where the wind suddenly picks up in speed, the machine starts paying attention to coronal holes. And 5 days prior to a slow wind event, if you will, the machine is looking at active regions. I mean, dominantly, it's not like a binary, it's looking only at, that's, it's a more complicated answer than we had originally thought. So here, for instance, is an example of this. So what we say is this is day 1, day 2, day 3, day 4, day 5. These are those images that I said from the sun, the coronal images. This is a coronal hole, this huge thing here. These bright points here are active regions, magnetic regions. And you can see the magnetic region is rotating on the disk. So the whole system actually, sorry, including the hole, is rotating from left to right. So the sun is rotating. And basically we try to predict, so this is day 1, day 2, day 3, day 4. And we are predicting the wind at day 7. We're saying, because it takes a certain amount of time. So day 7. So 3 days prior to a fast wind event, where the wind speed, we know the wind jumped to 600 kilometers per second, the machine starts looking quite closely at this coronal hole. So it suddenly lights up, right? So the machine is noticing that the fast wind, in this case, came from this region. Similarly, for slow wind, there's a slow wind event in day 7. You can see that the machine is generally paying attention to active regions, different active regions continuously all through. So I mean, okay, unfortunately, the conclusion we drew, not unfortunate, but I mean, the conclusion wasn't as strong as, it's like a nice little, bow. I wrap it up in a little gift and say, okay, here's the answer. It's not quite as dramatic as that, where you get a good reasonable correlation of 0.55, where you say like, okay, what is the probability, or what is the correlation between the coronal hole and the properties and the fast wind and the active region and the slow wind and so on. So it's well correlated, but it's reasonably correlated, if you will. It's not tremendous. Okay, so that's the solar wind thing. So I just want to say a little bit about what we're doing right now. One of the hardest things with machines is machine interpretation.
We are running out of time a bit, so can you wrap up in a couple of
minutes? This is my slide. This is my last slide. Can I have 1 minute?
Sure, please go ahead.
Yeah, it's my last slide. So, the thing is, we basically want to interpret machines. We want to train it to do something. If it does it well, we want to interpret them. It's very, very difficult to interpret a machine. So there are lots and lots of challenges that we've been working through over the last several years. And so I think if there is more interest in this, and from a physics point of view, I think we'll see progress in developing techniques to do this better. So there's a number of problems that I just want to highlight. One thing that, there's like things like super resolution, there's building vector magnetic fields from scalar data and so on. But one thing that I'm excited about that we're working on is we have a century's worth of solar data. And a lot of that data is very poor quality data, or not poor quality, but it's, it lacks some of the pizzazz, if you will, of the modern space-based, data. And so what we can do is we're building machines to take those past data and reprocess them in a sophisticated way so that we get high quality, a century's worth of high quality data from this. And so that's ongoing efforts that we think have a reasonable chance of success. Some of those machine interpretation problems are still ongoing and not so easy to do. With that, I'd like to wrap up. Thanks.
Well, thank you, Shravan, for this fantastic talk. And we had 3 very different talks in this session. The first one giving us some overview of the hardware specifications and what is actually going on where we run our codes. And then Prateek giving us a very wonderful overview from the user's perspective of large-scale MPI-based simulations, and Shravan attacking the problem from a different point of view when you have large data sets and we had to process all this data and do some machine learning, which a lot in the community is getting into now. So I'll thank you all the speakers now. We had some time for discussion, but I think we are running late. So I'll just take a few questions for this and then end the session and then go to the next session. So I see some hand up. I'll ask Dipendu to unmute yourself and then ask a question.
Okay, can you hear me?
Yes.
Okay, so Shravan, so I was curious about the comparisons you drew between kind of computational models and machine learning models. So here is a sort of a philosophical take on this, and I'd like your opinion on this. So just like in computational models, which is, let's say, trying to address a phenomena with different levels of approximations and complexity, one can also develop machine learning models for predicting a phenomena with different levels of techniques, different complexities, different neural nets, right? But however, as opposed to a computational model where we have an a priori understanding of the limitations of a model in terms of the approximations made and the physics that is missing, it is difficult to judge which machine learning model is better than another a priori, right? So the only recourse then being to compare the prediction skill scores a posteriori. So, given this context, is there a self-consistent way of judging before you even begin a work to understand what algorithm one can use specifically to address a certain phenomena, which is better than others?
It's a good question. I take slight disagreement with you on one aspect, which is to say that in a lot of cases we don't actually know what assumptions are creating problems, even in sophisticated numerical simulations. And
that's your opinion, but let's have the modelers have their opinions on that.
I'm not.
Question is posed from the machine learning perspective, right?
Yeah.
Do we understand what model to use a priori, which in my mind is a difficulty.
I think if you have a lot of data and you have a well-posed problem, then you can certainly use, they're parallel efforts, honestly. And it's not to say, I'm not trying to discredit numerical calculations, certainly.
No, this is not really, one versus
sorry,
another, of course.
Sorry, debate 1 second, let me finish, please.
Yeah.
I'm not trying to discredit in any way numerical efforts, or that's not my goal. What I'm saying is these are parallel efforts, and both have their, as you pointed out, their drawbacks and their positives and so on. If you have a lot of data, so that's a critical thing with machine learning. You need to have good data. You need to have a lot of data, and you need to have a well-posed problem. You need to know exactly what you're trying to do, connect with what. If you're able to pose such a problem, then machine learning works really well. And in tandem, there are lots of problems where numerical simulations are probably way better than machine learning.
No, Shravan, sorry, that was not my question. My question was, given the plethora of machine learning techniques, is there a priori method of judging which technique one can use?
Which machine learning method? Is that the question?
Is this something that you appreciate only a posteriori after you have got the prediction skill scores?
I'm not fully understanding the question. Perhaps we can take it off.
Yeah, we can discuss this later.
Okay, thanks, Dipendu. Bhargav, you have your hand up. Do you have a question?
Yes, if I'm allowed to ask one.
Yeah, quickly, in 1 minute, maybe.
Yeah, 1 minute. Okay. Shravan, an excellent talk. I enjoyed the aspect of machine learning that you have demonstrated. I have just one particular question regarding the prediction of solar wind that you have said.
Yeah.
There have been already a lot of discussions about the coronal holes basically are one of the main drivers of the fast winds. And that is something what you also are actually predicting over here.
Yeah.
But one thing I would like to understand from your perspective is that whether such machine learning tools can help us to understand how these solar wind will propagate throughout the heliosphere, or is it basically only accurate up to the point that you have data at L1, so you only will be able to do some sort of justice from the data at L1 itself, and not
exactly as you said. If you have data in throughout the heliosphere, then yes, then we can try to say something about what's happening at various locations, in the heliosphere. Unfortunately, at least between the sun and the earth, the L1 is like the best point that we have, right? And it's kind of the only point. So what happens between the surface of the sun or the corona and the L1 is anyone's guess. It's not really anyone's guess. That's where numerical simulation would work extremely well. And then you have clear connections between the two.
Okay. Right. That's it. I just will
stop. Thanks, Bhargav. So I don't see any hands up. So we had initially planned for a short discussion with all the speakers after this session, but we are running a bit late, and I don't want to disturb the schedule of the following sessions. So let me all the speakers are online. So let me just thank all the speakers now again for coming and accepting our invitation and delivering their talks, for giving us a wide spectrum of information about what really goes on in the landscape of HPC usage, as well as developing HPC hardware technologies. I had picked up a few questions from Sharanya and Prateek on the session one Slack channel, and these were mostly directed towards towards maybe Dr. Sanjay Wandekar. So Sharanya and Prateek, can you quickly unmute yourself and ask those questions here, and then we can conclude this session and reconvene in 5 minutes again for the Bindu talk.
Yeah, mine was a pretty standard question. I mean, nothing important said that much. So my question to Sanjay is CDAC planning itself, is itself planning to upgrade its supercomputer under NSM mission? Because one of the benefits that CDAC has for users at least is that it's a powerhouse of technicians who are experts in computational techniques, and anyone can apply for an account and get it. So there's nothing like a 60-40 thing as of now. So in that sense, it will be very beneficial if CDAC itself continues to provide supercomputing facilities in the near future.
As I showed in my presentation, we are actually set up one 200 petaflop AI petaflop system. Okay. That is mainly for AI and deep learning applications. But certain applications which use GPUs can utilize this system. And that is actually already up and running. Only thing is we are not yet released to the users, which is actually going to come up in sometime in April. So that is one system. Another system of general purpose HPC of 20 petaflop is expected to come in another 2 years timeline. Okay. But currently we are only coordinating the efforts of giving the users access to the various systems across the country. So I don't see any problem in getting access to these NSM systems for any users. And any help is required in that front also, CDAC is ready to help you out in those systems also.
Sanjay, maybe I'll just ask a quick question here. So now since we have the NSM distributed all over the country at different institutions, what is the plan? For example, if a person from Kerala wants to use a machine, will they have to approach the NSM system set up somewhere in Bangalore? So is it regional based, or anyone from any part of the country can access any machine?
Right now, since there are limited systems available, so we are giving from across the country, but we are trying to do it regional based so that the nearby institutions can utilize what is available locally. So that is what is the plan. But currently we have only four to five systems available. So we try to do that based on the requirement, and if the user is near, we try to give the access to the nearer system. That is what is happening currently.
Are there any, say, calls for proposals where you submit, or it is around the year, so you can submit anytime a request?
You can submit anytime. I think that is right now we don't have any mechanism of giving call for proposal. Maybe we are coming up with that when the higher compute power is required for a particular user, and maybe dedicated kind of requirement is there. Such users, I think we may have to have call for proposals, and that is will come up once the sufficient compute power is available.
Okay, thanks, Sanjay. Prateek, you had a question?
I just had one complimentary question to Sanjay, if I'm allowed to ask.
Yes, please go ahead.
Yeah, actually, this question is basically with regards to developing a visualization cluster in CDAC as well, because as Prateek also demonstrated very nicely, that visualization at least in astrophysics, and I'm sure that in all aspects of physics and biology, visualization plays a very, very critical role. So is CDAC actually planning to develop some dedicated visualization cluster in long run, or is there any thought given in this direction?
That anyway plan is there in terms of visualization, but right now current systems also there are GPUs available, and So certain softwares we have kept it, but I think some more improvements are required definitely. So we are working on those things. So certain things are already available, but for future enhancement are going to be happening shortly.
Great, thank you.
Pratik, you had a question?
Yes. So I was actually, I just meant, I think it was Sharanya perhaps who said that, primarily a lot of modern supercomputers have GPU components. That's actually not generally true. For example, I think Fugaku
I think it's Dipanjan's points.
Dipanjan's point, sorry. Yeah. So there are like, Fugaku, which is totally ARM-based CPU cluster. And I think, my feel for having sort of from very far away seen all this landscape is that there is need for everything. You need purely CPU, purely GPU, hybrid. Diversity is very much the need, because as a user, I have a code which I really can only spend some time to tweak. I cannot write a new code for very, very frequently. So we should have a diversity. And if you are best suited somewhere, you go there, right? I think I would like to hear Dr. Sanjay's take on that.
Yeah, so definitely, I think I agree with you. That's why we, in the current NSM systems, we have given 70-30 as a ratio. So 70% compute power is completely CPU based and 30% is GPU based. So let's say I have a 1.3 petaflop system where 1 petaflop is completely CPU based and 30% like 300 teraflop is GPU based. So that is what is the ratio we have kept in the NSM systems. I was talking about another facility with the CDAC, which is mainly for AI, deep learning, and other things. There we have 100% GPU based system. So this diversity we are also maintaining, because we understand all the applications are not running on GPUs, and that's why CPU requirement is much higher than the GPU at this stage.
Now, the reason I had asked this question was, at least from the European point of view, when you go to exascale, people are forced to go to GPUs mainly because of power limitations. And that is a big problem for us software developers, because we are yet to catch up. Most of the codes are MPI based, or based on CPUs. And this is a big problem for us. So one last question I found on the YouTube that's been conveyed to me, maybe again, this is for Dr. Sanjay. Are we considering FGPA instead of GPUs in any of the clusters? FPGAs.
FPGAs we have not yet started, but we have a certain core GPUs which were there in our earlier Param machine, and in the new system also we may plan certain FPGA based accelerators, but right now it is not available.
Okay, thank you. So let me just conclude this session and thank again all the speakers, Dr. Sanjay, Pratik, and Shravan, for taking the time and giving this wonderful overview of the work they have been doing. And then let us thank all the speakers, and I'll pass the baton on to Bhargav, who will chair the next session, starting with the talk with Dipendu.
Thanks, Dipanjan. Yeah. So we can start with the next session, and the first this session is about numerical simulations of solar and stellar physics. And for the first speaker, we have Dipendu. So Dipendu, I'm going to make you the co-host for this session for the first talk. Dipendu?
Yep, I can hear you. Yeah. I'm just going to share my screen.
Okay, Dipendu, I will. There are four talks in this session. I will essentially drop your chat message 18 minutes, so that you have 2-minute buffer time to actually end your session, and then we will have 5 minutes of discussion after each talk. And I would request all the participants who have also been connected in the session 1, and now we go into session 2, to please keep on interacting in the Slack channel. If you have any questions with regards to session 1, you can direct to each of the speakers. The expert speakers will try their best to answer those questions. And for session 2, if you have any questions, please drop your questions on the Slack chat. Okay, over to you, Dibendu. Dibendu is going to talk about star-planet interactions, space weather to exoplanets. Please.
Okay, so first of all, can you share my can you see my screen?
Absolutely, we can. Absolutely.
All right, great. So thanks for this invitation to speak in this session. So let me start off with a few general remarks in keeping with the earlier talks. So, I have worked in various solar physics problems, space weather problems, using different tools, starting from simple models to data analysis to more intensive computational models. And often what is lost in the overall general community is that computation is the third pillar of natural sciences, along with theory and observations. And in astrophysics, this is particularly important because we are often dealing with systems which are far away, where we are only being able to observe this remotely. And to extract adequate physics of the system, computational models is a must. And in this context, I believe that this workshop is a particularly great initiative. And given that our community is small and few and far in between, I think it's important for us to kind of get together and figure out what's going on with the community and also aid each other in our endeavors. And I hope that this is something that is not just the first workshop, but will in fact repeat in every ASI meeting from henceforth. So I'm going to talk about an initiative that we began in CESI about 3-4 years back to try and develop computational models of different levels of complexities to understand the space environment around Earth and other planets, with the need to kind of fill in gaps that exist in our country in terms of modeling expertise for understanding space weather, for space weather predictions, as well as for modeling the environment of solar system planets and exoplanets. And in this endeavor, I have been supported by various students who actually perhaps know more than me in some of the problems that they have worked in. And I would also like to acknowledge some of the students who are named here, as well as the community. And you see Bhargav Vaidya's name here, who is one of the developers of Pluto Code. And I think this is a great opportunity to provide our acknowledgement to him for helping us understand the Pluto Code in the initial phases when we are developing some of these modules for understanding the solar system space environment. Okay, so the sun's activity varies. It's not a constant star. And this is the case for other sun-like stars in the universe. And this variable activity in terms of the solar wind output, solar magnetic field output, forces planetary environments. And it is expected that this kind of a scenario exists in other astrospheres and exoplanetary systems as well, where the parent star sort of forces the atmosphere of orbiting planets. To understand this kind of interactions, star-planet interactions, one need to take recourse to computational models in order to understand the physics and be able to predict the impact of stellar activity on planetary atmospheres. So a classic sort of example of this interaction is provided by the sun, where we see various space weather phenomena such as solar storms and coronal mass ejections originating in the sun, impacting the heliosphere and planetary atmospheres. So our aim has been to understand the origin of these space weather events, model them, and then subsequently utilize this forcing of the sun to understand their influence on planetary atmospheres, which has implications for planetary habitability, not just in the solar system, also in other exoplanetary atmospheres. So one of the major impacts of the activity of a star is on the atmospheres of planets and in planetary atmospheric erosion. So the way this progresses is that the high energy radiation of sun energizes the upper atmosphere of planets in a way that they can escape the gravity of the planet, and then the solar wind catches hold of them, and due to a coupling between the wind and the atmospheric particles, they are eroded away. And this is a process that goes on throughout the evolutionary history of star-planet systems. For example, this is something that has been going on for over the history of the solar system of billions of years. However, this process is also influenced by either the presence or the absence of a magnetosphere, an intrinsic magnetosphere in the planet. And I will highlight how important it is to be able to understand these interactions so that we can understand in a better way one very neglected aspect of habitability, which is the presence of planetary magnetospheres. So what I'm going to do in this particular presentation is not to tell you in great details and go into great technical details about a specific problem, but provide you a flavor and a glimpse of the kind of modeling that we've been doing at SESI, ISER Kolkata, in order to understand the origin of space weather, the activity of the sun, and influence of this activity on planets in the solar system and beyond. So I will first highlight our efforts to model the sun's coronal magnetic field, which produces solar magnetic storms and the solar wind. Second, I will highlight modeling of exoplanetary atmospheres or planetary atmospheres, which has an intrinsic magnetosphere, for example, Earth. And then I will highlight the impact that a strong solar magnetic storm has on the atmosphere, or rather a magnetosphere of Earth-like planet. And finally, I will talk about some very recent results that is just coming up in monthly notices this week about simulating the space environment of Mars and the imposed magnetosphere of Mars to understand the atmospheric mass loss and the lack of the Martian atmosphere. So a little bit about the physics of the kind of domain that we're dealing with. So we're dealing with a domain where we have highly ionized plasma in general. This is more true the closer we go to the sun. And typically you deal with the subject of magnetohydrodynamics in order to understand and model this kind of a domain. This requires certain approximations. For example, your time scales must be much larger than the collisional time scales. Your length scales must be much larger than the device length so that you can treat most of the domain as a single fluid. We are not dealing with a relativistic system. So with this kind of approximations, you can apply the understanding of the MHD system to understand the sun-Earth or star-planet interactions. We are, of course, also dealing with a range of length scales and time scales, and this really depends on how global your simulation is, right? So this requires very intensive computation. However, often, and this is something that is important for the community to realize, and I think this has been talked about in earlier talks by many people, you can always define what complexity of a model, how computational intensive model you need to choose for addressing situation is something that is dependent on the problem that you are addressing. And if you can intelligently, with physical intuition, reduce the system to a more tractable numerical problem, this is often much easier. And the first problem that we'll highlight is something that shows that physical intuition can often triumph over brute force, very large computational simulation. Just going a little bit deeper to the computational challenges of a typical star-planet system, when you are dealing with activity, the origin of stellar activity close to the sun or its interior and the surface, you are dealing with a high plasma beta domain where the gas pressure dominates, and therefore the plasma flows dominate the magnetic field dynamics. When you go out to the outer atmosphere of a star like stellar coronae, domain changes to a low plasma beta domain where the magnetic pressure dominates, and therefore it is the relaxation and the dynamics of magnetic fields that influence the motion of the plasma. And finally, when you go beyond what is typically known as a source surface or Alfvén radius, it's the solar wind which dominates. So therefore, there again, the plasma beta becomes higher, and the magnetic fields of the sun basically are directed by the profile and distribution of the solar wind. So this sort of already tells you that modeling this whole system simultaneously could be a problem. And therefore, you often break this domain up into different subdomains and try to understand and predict the systems separately. But then you can also couple these different domains through boundary conditions and drive multiple models. That's another level of complexity. Let me first highlight a problem that we did. Over the last few years, we developed some understanding and a particular technique to model the solar corona. And I might also add here that Shomarajun Dash is going to talk more about this approach in workshop 6 on 19th February. Okay. So this model is a simplistic model which is based on physical induction of the system. So what you understand is that magnetic fields in the sun's outer atmosphere are rooted to the solar surface, and their movements due to photospheric foot point motions drive the dynamics in the upper atmosphere, where the relaxation and reconnection of the magnetic field and its quest to reach a minimum energy configuration drives the dynamics. So to predict the solar corona, then one approach is to provide data-driven models for the sun's surface and couple that to, for example, a potential field source surface model of the corona, which essentially is based on this energy minimization, to develop a very efficient algorithm for predicting the sun's corona. The advantage of using data-driven surface flux transport models for the sun's surface is you can predict the sun's surface in advance, many days in advance, and then utilize a coronal field extrapolation model coupled to that to predict the sun's corona. So we have utilized a surface flux transport model that utilizes magnetic fields observed on the sun's surface to drive surface flux transport evolution. And then based on this, we infer the future solar magnetic field on the sun's surface and couple that to a potential field source surface model to generate the solar corona. And we've tested this technique now over 3 different eclipses. I am just providing here one of the examples of our simulated output with the background corona observed during the Great American Solar Eclipse of 21st August 2007. In particular, I want to highlight that we could successfully predict 2 major streamers, these are known as streamer-like structures, and 1 pseudo streamer in the coronal field. Whereas another group from the US who are using a much more complex full-scale MHD model and the third fastest supercomputer in the world, the Stampede cluster, could not predict this pseudo streamer, which we rightly got. And the reason we got this right was our utilization of a surface flux transport model, which could also predict the high latitude fields much more accurately than just using an observation of the magnetic field, which was used in this model, because in these observations, the high latitude fields are compromised due to position effects. Whereas in our surface flux transport model, we can generate that very effectively. All right. So next, I move on to understanding the Earth's space environment. So here, what you see in the background is an example of a simulation that we have done utilizing the star planet interaction model developed at Pluto, which is a more full-scale, more complex model, which depicts the solar wind forced Earth's magnetosphere with a bow shock in the day side facing the sun, a magnetoidal structure in the night side, which is formed due to magnetic reconnection between the stellar wind magnetic fields and the Earth's magnetospheric magnetic fields. And this tells you that the presence of this bow shock, which literally stops the solar wind and the stellar magnetic fields here, protects the Earth's atmosphere from erosion due to the sun's magnetic field. This is apparent. The star-planet interaction dynamics is apparent when you look at how different speeds, different strengths of the stellar wind speed impacts the magnetospheric standoff distance. So what you see here is the Earth and depiction of simulated magnetospheric standoff distances. And what you see here as the solar wind speed increases, going from here to here, the magnetospheric standoff distance becomes closer and closer to the Earth. perhaps already telling you that what this implies is if the Earth's magnetic field is weakened, or the solar magnetic field strength or the stellar wind speed is much larger, then more of the Earth's atmosphere can be exposed to the solar wind. So this also provides an opportunity to understand the impact of a magnetic flux flow, which is embedded typically within a solar storm, like a CME or a coronal mass ejection, when it travels from the sun and impacts the Earth's magnetosphere. This is a simulation that we have been also doing, where first of all, this is something a work in progress, where we are considering an idealized Goldie Hoyle flux flow to mimic a CME structure, in the sense that we have the sun, we have the Earth, and then we have a flux slope traveling embedded in the solar wind, which then impacts the Earth's atmosphere. We have to make several assumptions, which are stated here, in order to be able to simulate it in a more simplistic way. And I will not go into details of that, but I'm happy to discuss that later. But this is the impact. What you see here is a view from the plane of ecliptic of the current sheets, the strong current sheets that developed in the magnetosphere and the magnetotail when a strong magnetic flux slope, which is part of a solar magnetic storm, hits the Earth's atmosphere. And this view is from the north pole of the ecliptic. In the bottom, what you see here on the left-hand side is satellite observations, typical satellite observations of a magnetic storm. The typical magnetic structures, the different components of the magnetic field that you see. On the right-hand side is the same different components of the magnetic field acquired from what we call a virtual satellite. A virtual satellite is a point placed in the simulation where you wanted to place it and estimate the time dependence of the different magnetic field parameters as it passes by, as a storm passes by. And what we find is that we have pretty much the qualitative features well reproduced, particularly this beautiful rotation of the BY component of the magnetic field that you also see in the observations here. Okay. Finally, I want to highlight this problem of Mars. So understanding how an intrinsic magnetosphere or lack thereof impacts the loss of planetary atmospheres and habitability. So I want to first set the context here. And often when you're trying to do a numerical simulation, you want to understand what is it that you want to understand, what is the problem that you're setting up to deal with your model, right? So the thing that you understand about planet Mars is when it was about 1.5 billion years old, young, it had a liquid iron nickel core with strong rotation, and the fluid motion could sustain a dynamo action. And therefore, Mars had an intrinsic magnetosphere which was strong enough to shield the surface atmosphere and water from the solar wind. So it had sustained greenhouse effect, it had a warm, moist atmosphere, which some believe was suitable to harbor life. Then something happened. The liquid core of Mars froze, and the dynamo action stopped, and Mars lost its magnetosphere. And if you look at the present day Mars, it is a cool, thin atmosphere rich in carbon dioxide, which is deemed unsuitable for life. Okay, we wanted to simulate. So here is a simulation of the interaction of the stellar magnetized winds, the solar winds, with a young Mars, which has a magnetosphere. And I want to draw your attention to the x-axis here, where you see the magnetospheric standoff distance is about 5 Martian radius away towards the day side, therefore protecting everything that is inside. Now, what you see here is when Mars does not have an intrinsic magnetosphere, simulation of a present day Mars. What is interesting is you still see there is an imposed magnetosphere, which is not intrinsic to Mars, has been imposed by the draping of the magnetic field lines of the sun, which is carried by the stellar winds around Mars. And here is like a pseudoscalar stressing of the flows around Mars. And you see that the solar wind still doesn't penetrate very much, very close to the surface because of this imposed magnetosphere. However, the devil is in the details. If you look at the, this is too tiny even for me, my eyes. if you look at what happens to the magnetopause, the distance of the magnetopause from the interior of the planet, when you have an intrinsic magnetic field, which is this case, you have about 5.4 times Martian radius. When you lose a magnetosphere, when you don't have an intrinsic magnetosphere, but you only have an imposed magnetosphere, this reduces. Now the magnetopause is only 3.8, 8 times the Martian radius, and therefore it's come closer. However, the more interesting physics actually happens when you look closely at what draped field lines in the Martian imposed magnetosphere is doing. So what you see is, if you carefully look at this dynamics, is here, well, the background is just the density. This white field lines are the stellar wind field lines which is draped around Mars, creating the imposed magnetosphere. Blue field lines are the field lines which slip past Mars and is in the Martian magnetotail. What we notice is this slippage of magnetic field lines from the imposed magnetosphere around planet Mars is occurring dynamically all the time. And therefore, if you do not have an intrinsic magnetosphere but an imposed magnetosphere, there is continuous exchange of fluids along with the field lines from the Martian day side to the Martian night side, implying much more of the Martian magnetosphere is being lost through the solar wind. So this tells you the importance of having an intrinsic magnetosphere, for example, for a planet like Earth, for habitability. Because if you lose it, then you are much more susceptible to loss of the atmosphere. So this is my concluding slide. So I can just read it out here, that the activity of stars shape planetary environments. And taking the solar system, the sun, the Earth, and solar system planets as a test bed, an example, they have developed several numerical approaches to understand dynamic magnetic activity of stars and their interaction with planetary magnetospheres. As I said, we have just begun this work over the last 3-4 years, and this motivation was with developing something that is lacking in the nation. And we're constantly learning and improving our techniques from more simpler to more complex models. As we do that, and as we have demonstrated, we are opening up ways to understand space weather near Earth and the habitability of planets, both in the solar system and beyond. Thank you.
Thank you, Dibyendu. It was a very nice introduction and a very nice demonstration of the models that has been developed at SESI, demonstrating about how the planetary environments are shaped because of the effects of the sun. We have time for some questions. Please, participants who wants to ask question can raise their hands and they can ask their questions. We'll wait. That is okay. Do not raise hands. So there is one question by Viren. He's unable to. Viren, can you unmute your mic and tell your question? You can wait. I'll try to see if I can unmute your mic. Now you can unmute.
He has a microphone problem, he says.
Okay. So I can.
He can type it down, right? He can type the question, and Bhargavi can read it out.
Yeah, I'll basically read it out. It says, I have a question, but I'm not able to. Okay. I have a very naive question. Space missions like Aditya L1 and Parker Solar Probe, as far as I understand, collects data from the sun. But we know that certain complex features of the sun are still not visible to us. Can we shoot a large amount of accelerated charged particles toward the sun to trace its path to make these features visible, much like how sun throws winds of charged particles towards us, which allowed us to study the magnetic fields as such?
Well, that's a novel question. I'm not sure about that. Because you have to understand the energetics here. I mean, if you're throwing something at the sun, what scale would you throw it? You are saying that you want to throw it at a scale that you want to get out the fine scale structure. If you do not have an instrument that is capable of resolving that fine scale structure, even if you throw something at the sun, which may generate a phenomena to illuminate that fine scale structure, how would you even remotely image that? So that's a problem that is something that we astronomers have come to live with. For all, for the model validations, we typically have 1-point measurements, right? If I want to validate my global models of the Earth's magnetic field forced by the solar wind, or if I want to resolve the global structure of a magnetic flux slope, which is part of a solar storm, I am at best saddled with 2-3 satellite observations, which are 3 minor points, which doesn't give you a global picture, right? So I tend to think of this in a different way. I like to see it in a way that let's try to get the physics right, build these global models, then extract parameters from this model at a point where a satellite is sitting and see if I am able to match those observations. Of course, if you have multi-point observations, then you have much better validation of the models. So that's the philosophical approach we take.
Okay. We have one question from Pratik. Had one question, Pratik. Pratik, you wanted to ask one question? I'll unmute you. Pratik, I've asked to unmute you. While Pratik is preparing, maybe Mayank can unmute. You can unmute Mayank.
Hi Devendu. Yeah, so I have this question from the exoplanet side. So how good are your models at, let's say, modeling the solar wind? Because now there's a growing consensus in the exoplanet community that the stellar interactions with the, let's say, planetary magnetic fields can, let's say, produce radio emission or UV emission. So how good are your models at, let's say, modeling an M-type star or let's say a K-type star?
All right. So just to clarify, to remove any doubt, we are not self-consistently modeling the origin of the solar wind and its influence or impact on planetary magnetospheres. We are assuming a solar wind with the properties that they're observed in this particular kind of models that we have shown. There are self-consistent models of the solar wind that can also be developed. Typically, this is the current understanding, and there's been a lot of work because, as you said, it's a big problem in the scientific community in the solar stellar side is to understand how does the solar wind speed, solar wind magnetic field, and the solar radiative flux changes with a solar-like star at different levels or over the evolution of the sun, so that we can understand how this interaction has happened over planetary evolutionary timescales, so that we understand how has this shaped the evolution of the habitability of planets. So there are particular scaling laws which has been derived from stellar observations which relate the solar wind speed to, for example, a stellar rotation period. So if you give me a star whose nature I know, in the sense if it's a solar-like star, is it an M-dot star, and I know its rotation rate, I can give you an empirical understanding based on observations again and some modeling also, how the stellar wind speed would scale with that. And yes, there is now an important, direction of study in trying to understand the interaction between stellar winds and planetary magnetospheres in extraplanetary systems. Look at if that interaction, for example, a radio emission, auroral emission, or even, for example, mass losses. So it turns out that in H alpha, not H alpha, sorry, helium line is a very good tracer of mass losses.
Yeah.
Can you actually figure out the planet has an atmosphere or even a magnetosphere through these processes, right?
Mm-hmm.
We have done those calculations. In fact, in our first paper, Varga would know that we did a calculation on the radio power. Those powers are too low to be able to detect from Earth. We are working on that to understand what, in fact, Shovik is one of my students who's speaking, I think, in one of the sessions. Is looking at a scaling between the stellar magnetic field strength and the planetary dipole strength to see at what level will it give rise to a emission that could be detectable from Earth. It's not looking very promising at this point in time, unfortunately.
But maybe,
Mayank, we are actually having a little bit short of time, but what I suggest you, Mayank, Anindya,
we can take it over.
Vagesh, please put your questions on the Slack.
Yeah, sure.
Unfortunately, we do not have time to cater to more than 2 questions just after the speakers speak, and we have to move ahead. I would like to thank Dipendu once again for a very nice talk. And now we will move over to Piyali for the next talk. And I would request all the other participants to please put their questions over Slack or YouTube. We will be catering to them in the discussion session when we do that. Piyali, you are co-host now. Piyali?
Yeah, thanks. I'll just try to share the screen.
Yeah, thanks, Piyali.
Just, I hope you can all...
Piyali, we can very well see your screen. I will give you a warning at 18 minutes, 2 minutes before your talk to wrap up. Thank you so much.
Great.
Please,
okay.
Go ahead.
Yeah, so thanks to Sharanya, Bhargav, and Dipanjan for having me in this session. And I would be speaking on a subject much more closer to the sun. So the solar atmospheric dynamics through MHD simulations. And I also like to start from this picture to motivate the range of spatial and temporal scales, and also the values, the large range of values of the plasma beta that is present from closer to the sun to the solar heliosphere. So essentially near the sun, you will have flux emergence, which will be leading to solar flares, eruptive phenomena. And then there are these high energetic particles and magnetic clouds, which would ride on the solar wind and reach closer to the Earth's magnetosphere. So, so far, there does not exist a single model which can, span from the solar interior to the ionosphere of the planets, specifically of Earth. So this is because of this issue with the range of scales present. However, there are efforts being done to develop what are known as plug and play models. So these are the sequence of models, the output of which becomes the input of another. So we have these, different models. So I would be mainly talking about the solar atmospheric models here. So using a tool known as the pencil code. So as you can see, my initials of my name are same as the pencil code. So we have these different features of this code. It's a 6th order finite difference code. And it's very, it's quite cache efficient because it's the computation is done in pencil. So there's a reason why this is called the pencil code. So if you have a data cube, so the data cube is broken down into one-dimensional pencils, and all the mathematical operations are done between two pencils. So that is what makes it very cache efficient. And this is a fully compressible and parallelized code, and it works in a modular fashion. So there is a central engine, and there are several modules which we can plug in and plug out depending on your physics needs. And there are several coordinate systems which one can avail of. So there's the cylindrical coordinate system, and of course the Cartesian and spherical. You can opt for uniform and non-uniform grids. We presently don't have adaptive grids in the pencil code, but we do have these other static grids. There's a radiative transfer module, but using the local thermodynamic equilibrium opacities. So one of the unique features of the pencil code is that it's a multi-user code. Presently, we have over 200 users and 50 active developers. And it is maintained as a live repository on GitHub, which basically means that suppose today I develop a new module or a new, or I update my code and I check it into GitHub, you can immediately access the changes to the code. So it can be a new initial condition, a new boundary condition, new module, it could be anything. So this code tree on the GitHub is typically updated 5 to 10 times daily, sometimes more. And we carry out regular sanity checks, hourly, nightly, and weekly auto tests. So we have a suite of example problems which are tested to check that no one has broken. All the users, some of the users have not broken anything in the code, and everything is consistent. So because of this, can you still hear me? Hello?
Yes, we can hear you.
You can, yeah, because maybe my screen froze. Okay. So for some reason, yeah, okay, yeah, now yeah, okay. Yeah, so because of this large number of users, so the pencil code community is organized into users, developers, and owners. So when I started first with the pencil code more than a decade ago, so I was a user, but now I'm an owner of the pencil code. So you can move up the chain depending on the amount of contribution you have done to the code. And there exists what is known as a pencil code steering committee. So it consists of 5 members who are selected, who are chosen through electoral votes for a period of 4 years. So the present pencil code steering committee consists of these members, including Axel from Nordita, Niels, myself, Philip, and Matthias. So we basically have started what is known as the pencil code office hours. So every second Friday of every month, we have these office hours for new and existing users who, want to seek help for their setups or have questions on how to, or have encountered some problem with anything related to the code. So they can come over Zoom and then ask for help from whoever, logs in besides the pencil code steering committee members. So with this introduction to the philosophy of the pencil code, so let me talk a little bit about to what application it has been put to with regard to solar plasma. So this is one of the codes which can handle eruptive phenomena of solar flares, as well as quiet sun phenomena equally well. So this is something which is a novel feature. So beside that, it can also be used for simulation of the solar dynamo, the direct numerical simulation of the solar dynamo. And if you go out into the solar atmosphere for coronal mass ejections, and there are other applications of astrophysical MHD, including protoplanetary formation of protoplanetary disks, gravitational waves, chiral MHD, galactic dynamos, combustion, and many more. So, but I mainly use it for solar plasma simulations. So the solar plasma, the solar atmosphere mainly consists of these 4 layers, starting from the photosphere. And then we have a thin chromospheric layer where the plasma exists as partially ionized. So there are a lot of neutral particles present there. And then there's a transition region where the temperature undergoes a steep change from 10,000 Kelvin to 1 million Kelvin. And then we have the corona, where the plasma beta is really very low, such that the magnetic field determines what the plasma does in that region. So this plot that you see is basically the stratification that we normally use, but you can use a variation of this. You can have your own stratification file. And on the rightmost part, you can see a movie of the solar granulation prepared by my student Shohel Day using this setup. And so basically he has plotted the vertical velocity, and then in the lanes, the intergranular lanes, the green and the blue regions are basically the regions where the magnetic field is quite strong. So those have been marked. And so in the solar atmosphere, there are some caveats. We can still treat the solar plasma as a single fluid here because the Debye lengths are small, such that the plasma per parameter is really large, which means that there are a lot of ions and electrons inside the Debye volume, such that the quasi-neutrality of the plasma still holds. The only problem is in the chromosphere, where the single fluid approximation tends to not hold quite true because of partial ionization and collisions between ion and neutrals. So this local thermodynamic equilibrium, which is also abbreviated as LTE, is not quite valid, as the radiation source function also deviates from the Planck function, the Planck's black body function, and scattering becomes important. So in the chromosphere, MHD is only an approximation. But if you want to do better, there are codes available to do that. However, it is of course very expensive and computationally expensive. So we might as well use a radiative MHD and try to see if we can get the dynamics of the solar plasma right. So these are the MHD equations in the pencil code. So we have the continuity equation in terms of log rho. And then we have the Navier-Stokes equation and the induction equation. So the induction equation is actually in terms of the magnetic vector potential, so which basically means that we don't have to worry about any divergence cleaning in the code. And this was done, this was initially done because the pencil code at its, when it was first written in 2001, the engine of the pencil code, it was made for solving dynamo problems. So in the dynamo, as you know, the magnetic helicity plays an important role. So the A dot B plays an important role. So that's the reason the induction equation was coded in this manner in terms of the vector potential. And the reason the density equation is, the continuity equation is in terms of log rho rather than rho, is to avoid negative values of rho in regions, which is actually particularly useful for application to the solar atmosphere. So I just wanted to say that this continuity equation is coded as a density module, the Navier-Stokes in form of a hydro module, and the induction equation is in the magnetic module. So these are different physics modules which are essential ones. And apart from that, there are these energy equations which can be used in several ways. So if you are interested more to convection problems, it is recommended to use the entropy module, which solves the equation for entropy. The first equation in this slide indicated by small s. But if you're not interested in convection, you are dealing with, say, like I am doing with the solar atmosphere, there's no convection involved there. So you might as well use the temperature module. So the temperature module solves the equation for LNT, again, the same reason, to avoid the temperature having negative values. And then you have these various terms, various heating and cooling terms available. There are these heat fluxes, the radiation, the heat fluxes, the radiative heat flux, which comes from the radiation module, for example, and the conductive heat flux, which comes from what is known as the heat flux module. So in the radiation module, so we solved the equation for detailed radiative transfer using the method of long characteristics described in this paper by Heinemann et al. We use the Gray approximation and neglect scattering contributions, which means that we can only deal with local thermodynamic equilibrium conditions. We integrate the radiative transport equation for specific intensity I over a solid angle omega. And S is basically the source function. You can see it defined as sigma T4. So that's the Planck's function integrated over all frequencies. And then we solve for this radiative heat flux. And then it remains to code for opacities. So in the solar atmosphere, the opacities, opacity sources are bound free. The scattering of the photon by bound free, and H minus processes. So, so the way the opacities are coded using Cramer's law and other fitting equations have been described in this paper, which is basically a code description paper. And another feature is about, so this was about the radiative heat flux. Now let us talk about the conductive heat flux. So as you know, in the solar corona, it's quite hot. The temperature is 1,000,000 Kelvin. And then therefore we have this anisotropic field aligned Spitzer heat transport, which means the heat transport along magnetic field lines is much, much faster than the cross field transport. Now, since the temperature is extremely high, so what happens is this coefficient kt to the power 5 becomes really large. So, so when the diffusion coefficient becomes really large, that has a bearing on the time step of the MHD code. So the time steps usually become really, really small when the flux reaches the free electron streaming limit. So we have a workaround on that. So what we do is we use what is known as a non-Fickian hyperbolic heat transport equation. This is also known as the telegraphic equation. So that's given in the second equation with tau s and qs. So we solve this partial differential equation for qs. And this is basically like a relaxation equation where we can choose what is our tau s, but we choose it such that the wave speed in this equation is less than the maximum Alvin speed in the domain. And besides, we also make sure that the diffusion velocity is, is limited to, 1/10 of the actual speed of light. Or the flux is basically a fraction of the free streaming limit. So this is also described in this code paper in GAFT. So now, so much for the equations. Now to close the equations, we of course need an equation of state, or EOS modules as it is called in the pencil code. So there are several EOS modules available, but I will just restrict myself to these 3 models which are given here. So the first is of course the simple ideal gas equation. And the second one is the equation for ionized gas, which is a combination of ideal gas equation plus Shah ionization equation. So then you have this effective mass, which is a function of the function of YH. YH is the hydrogen mass fraction in the solar atmosphere, while XHE is the helium mass fraction. So mu depends on the hydrogen and helium mass fractions. And we let this hydrogen mass fraction be governed by the Shah ionization formula. And then there is also an equation of state, which is ideal gas, but with a constant ionization fraction. So the ionization fraction does not change with time. But I will mostly use the first two, either the ideal gas equation or the ionized gas equation. Yeah, so then there are these numerical challenges that come along when you want to simulate the coronal plasma. And one of them is the small plasma beta. So what happens is the Lorentz force can make the numerical density become really small in certain regions. So to overcome that, we might need mass diffusion, which has its own limitations. So we always try to limit the mass diffusion in our codes, but sometimes it is inevitable. And then there is this problem of having the large Alvin speed in the atmosphere. So for a typical magnetic field strength of 200 Gauss or 300 Gauss in the corona, the Alvin speed can become almost 1/3 the speed of light. And at that time, we cannot neglect the displacement current in the Ampere's law. So we have to take some steps to contain that. So in some codes, people also try to artificially reduce the Lorentz force because this feeds back into the Navier-Stokes equation. The current, the J cross B feeds back to the Navier-Stokes equation. So artificially reducing the Lorentz force may lead to unphysical consequences for coronal heating. So what we have recently resorted to is include what is known as a Boris correction. So this is a semi-relativistic correction to the Lorentz force. And here we retain the displacement current in the Maxwell's equations, but we neglect the relativistic corrections in the Navier-Stokes equation. So the Navier-Stokes equation is non-relativistic, but the electrodynamics is treated more relativistically than by not neglecting the displacement current. So here are the equations for that. So the first equation is, of course, the Ampere's law. So normally in MHT, we only say J is curl of B, but now because of these large Alfvén speeds, the second term dE by dt also cannot be neglected because the Alfvén speed is becoming comparable to the speed of light. So then, so without neglecting this displacement current, if we write down the Lorentz force, there will be several correction terms. So in effect, what happens is in the Navier-Stokes, if you put them back in the Navier-Stokes equation, this essentially leads to an increased inertia of the plasma and a reduction, a natural reduction in the Lorentz force. So now we don't have to artificially reduce the Lorentz force, but have some kind of a physics basis for doing that. So here, what would happen is along the magnetic field lines, the equations are still hydrodynamic. However, for cross-field dynamics, the plasma experiences a larger inertia and the Lorentz force reduces. So then that is what governs the dynamics. And this is not artificial. This is what is coming through the correction because of this displacement current. So, so we have applied this pencil code to the phenomena of solar flares on the sun. And we basically looked at delta sunspots. So these delta sunspots are what are known as superactive regions on the surface of the sun, and they usually flare repeatedly. So it is important to understand why that is the case.
Yali, Yali, sorry to interrupt. You have just 1 minute left. If you can wrap it up quickly.
Okay, yeah, sure. So, so then we performed this first ever solar flare simulations, which produced observed flare energies. And this simulation was so once we start the simulation, we didn't interfere in any way by using any forcing or any boundary conditions. So really, in a very self-consistent manner, we had a delta sunspot forming because of collision of two sunspots and giving rise to repeated flaring. And this was, of course, different from past simulations because we could, we didn't use a flux tube, the concept of a flux tube emerging nicely from below the subsurface. Rather, we just put very simple horizontal layer and let it evolve in any way it wanted to. So we could produce these delta sunspot-like features and some properties of reconnections. And recently, we have applied this code to the phenomena of the solar spicule forest to understand the origin of the forest of spicules. So here, so this is part of my students' PhD work. So, so then we see these spicules forming that you see on the right-hand side in the movie. And as they form, they also twirl and twist around each other. So this kind of features are often seen in Hinode in the Hinode data as well. So they're quite ubiquitous there. And we wanted to know why that is happening. So we looked closely.
Really, can you just wrap it up quickly?
Yeah, I'm just trying to go to the next. So then when we looked quite closely into our numerical mimicry, we discovered what are known as coronal swirl tubes, which are basically what is responsible for these kind of twists in the in the solar spicules. So to summarize, in the context of the eruptive phenomena, so we have improved the pencil code to work efficiently for solar atmospheric simulations and applied it to solar flares. And then we have applied it also to the quiet sun phenomena, where we have reproduced the ubiquity and length of spicules much better than previous studies. And also discovered a new phenomena known as coronal swirls, which are responsible for twisting of spicules in the solar corona. So yeah, so that's the end of my.
Thank you so much, Piali, and it is very nice to see a very good introduction on pencil code. I think it is very, very important that participants also get to be aware of the different codes that are existing, and that was essentially one of the main purpose of this this workshop as well. So the floor is open for questions. In case anyone wants to ask a question, please raise their hands. We are running a bit short of time, so I can take one question. In case there are no questions, I can ask one question. Just wait for 1 second. Okay, it's not there, so maybe I can take a privilege of being the host and ask your question, Piali. I mean, you described about the way you actually put the conduction term in your and solve the temperature. What sort of, because you are very well aware that these are diffusive terms and therefore you will have issues with regards to the time stepping when you do it explicitly. How do you basically cater to such time varying nature of the diffusive term that you have for the conduction and the advection term, which you basically deal with your flow of magnetic fields or something like this?
So the advection, we calculate the Courant number for the advection separately. But as I told you that this thermal conduction term is little problematic if you want to directly include it in the energy equation. So what we do is instead we solve an equation for basically this equation here. So here the conduction term comes in here, and then we don't directly solve for it, but we solve this telegraphic equation where we say the flux is approaching the conductive flux, but over a time scale of tau s. So that does not constrain the time step of the due to this conductive.
But do you maintain stability of your algorithm within that tau s time?
Yeah. So that we can vary. And then we can check if this the solution looks similar to one where we have included this term directly in the equation.
And what about the saturated flux?
So the saturated flux, we have kept a limit. So this conductive flux, we don't allow it to become 1/10 of the free streaming limit. Okay. Where the whole flux is being carried by the thermal energy. So
I think there will be many more. We can have offline discussion as well, but we are running short of time. So thank you so much, Piali, for a very nice and a good talk on processes very close to the sun. And now we can go to the next speaker, Nishant. I have made you the co-host.
Hi, Bhargav. Others, can you hear me? Hello?
Absolutely, we can hear you well, Nishant.
Okay, I'll just share this. And let's see if you can see this.
Yes, very clear, Nishant. So I think without further ado, let's start the next talk in this workshop by Nishant Singh on self-consistent formation of sunspot-like magnetic flux concentration. Please, Nishant, go ahead.
Thanks, Bhargav. Thanks the organizers for this opportunity. And welcome you all. Many friends joining. So hello, everyone. So this is a work that has been in progress for some years now without actually reporting it. But now we are kind of finalizing this. This is on the theme of self-consistent formation of sunspot-like flux concentrations in numerical simulations. And thanks, Piali, for a very nice introduction to the pencil code. I was anyway not planning to do that, but it would help the discussion that is going. But this is first to just entertain some of you that the sunspots are known from very early times. And if you are interested in some controversies, then you can read a bit about Christoph Scheiner and Galileo, and fierce fight between who was the first to report the sunspot. Of course, these are the spots. These are the hand-drawn sketches, by the way. So very beautiful sketches. This is an example from Christoph Scheiner's sketching, where very detailed drawings of sunspots. In case you can see my cursor, you can follow. If you go onto the sunspot, one of the sunspot, and this is like the solar disk, and this is the modern day sunspot, which has a clear umbra and a penumbra, and these are the convection granules. Typical sizes involved are this tiny little granule on the photosphere is on the order of 1 megameter. Sun has a radius of 700 megameter. So this is just to put some numbers in context. And you can see that these drawings are actually like very detailed, and these were known as dark features on the sun, but they were not known as a magnetic features. So it was only very late that we came to know that these are also the magnetic fields, and these are the first observations of magnetic field outside the Earth. So only after the Hale discovery of Zeeman splitting. So yes, so these sunspots are essentially the first examples of magnetic field outside the Earth, and I'll argue that we don't know about the mechanism that leads to its formation, and that keeps this field very much alive and exciting. We also know, of course, that the sun undergoes a clear cycle of around 11 years from a phase of very high magnetic activity. These are the images of magnetograms, where the white and black are the two polarities of radially outward magnetic fields, outward and inward, white and black. So these are the intense phase. This is the intense phase of magnetic activity. And then the sun goes from large activity to a very quiet phase when there is no sunspot on the surface of the sun. Right now, like 2021, this is just coming out of its minimum. So the phases are roughly like that. And about 7 years, 5-6 years, you'll see large activity back again. And this is the so-called butterfly diagram. If you azimuthally average the magnetic field, count the, or just count the number of sunspots, it tends to migrate from high latitude to low latitude and forming a butterfly-like pattern. So all that is very standard. And and sun is not the only star. Pretty much every star has its own magnetic field, depending on what is the process that we perhaps don't know. But depending on the processes involved, there are very different kinds of magnetic fields in different stars. So this is one example of a magnetic field in a star where the radial field dominates much towards the pole, not so much towards the equator, unlike the sun where the phi field or the azimuthal field dominates the dynamo, perhaps, underlying dynamo. So I will, of course, not discuss anything about dynamo, but this is just good to know that dynamo is one mechanism that can produce the magnetic field on a range of scales by, for example, differential rotation or shear that is anyway present in the sun or other stars, that helps in stretching the and building some coherence in the magnetic field. And that field, it's also important to know that it is not very strong. The field that is produced by dynamo is not very strong, by the way. Okay? Sunspots are way too stronger than what dynamo can give you. Okay? So just to show that this type of observed butterfly diagram are nowadays routinely formed in a variety of different simulations. These are the simulations from, for example, the pencil code and a number of other codes. This is from Arnab's group, and this is Maushami Dikpati's group, Pipin. So there are many, many codes, as I wrote, different groups with different codes, with different physics altogether. Even physics is very different. What equations being solved are different. But nevertheless, they routinely produce solar-like cyclic solutions. So these butterfly-like cyclic solutions are now a very routine thing. But it's also good to note that the story started with this spot, right? And with this spot built this whole idea of some azimuthal dynamo wave and stuff. But none of these codes actually form a sunspot. These are global dynamo solutions, and strengths of these magnetic solutions can vary from code to code, can depend on some initial conditions and stuff. But it's interesting that none of these codes actually self-consistently form the sunspot. So the real question remains, what actually forms the sunspot? So that question, I think, remains unanswered in any of these simulations. And it's also difficult. So it's not that this is an easy problem. As you can see, the scales involved are huge when one is solving for a global setup. Resolving very small scales becomes a very challenging task with limited computing resources. This is not an easy thing. And that is why it is important, as Pratik was arguing, that you take one piece at a time. So for global cyclic solutions, you take a whole low resolution full sun solution. But when you are interested in some local physics like the sunspot, which you can argue as a local physics, then you better take a small piece on the sun and try to simulate that. So this is what is now done in this work that I'm going to describe. If you are interested in the setup details, then the very similar setup was used in this earlier study. So basically, one solves the full MHD equation. Piali has already shown all these equations, so I will not get into this. We are basically interested in turbulent magnetoconvection. So where convection is also driven self-consistently. We are looking at the entropy equation here with imposed flux from the bottom and fixed temperature at the surface. It leads to some entropy profile within the domain, which is supportive of the convection. You all know about this Schwarzschild criteria. So if the outward radial gradient of the entropy is negative, you will have a medium as convecting medium. So this is what all is in the background. The Rayleigh number in these simulations is large, very large, to enable turbulent regime of convection. And convection itself has been a very challenging and very interesting problem. I'll just show a few glimpses of these convection results as I go along. These simulations are large eddy simulations. This Smagorinsky type viscosity used. Also for the magnetic diffusivity, this is something that we just tried. Although in equations it's written eta, basically it is you consider replacing this eta by a Smagorinsky eta. Okay, and Smagorinsky eta you can further relate, just like the Smagorinsky viscosity is related to the square of the rate of strain tensor. This you can relate with appropriate Smagorinsky type coefficient, square root of the current density. So with that, this makes it a full-fledged large eddy simulations with both viscosity and diffusivity being on the same type of footing. So some 40 million CPU hours were used for just a couple of these simulations. These are very high resolution simulations, 1024 cube, that were running on 4096 cores that we got some time on this Brace machine. And we use the pencil code. This is an open source code, as Piali highlighted. Anybody can use. In fact, all the setups that I'm also going to describe is in fact all publicly available. So one can simply take up various setups. And if you think that is not available, you can just ask any of us. People are generally very friendly. So they'll just give you the setup and you can run. So this is as simple as that. So these these equations were basically solved using the pencil code. These are convection setups. Background in this turbulent magnetoconvection model will look something like this, that the density as a function of depth, you can see 0 is the surface and this is the depth. So it's like, I can show you, this is like a Cartesian box that is being simulated, where the horizontal extent is 100 megameter by 100 megameter and depth is about 25 megameter. So it's a relatively larger box. So 100 megameter by 100 megameter by 25 megameter. this is the convection granule pattern. This is the vertical velocity, as you see. Light color is like upward moving blob of plasma, and these dark lanes are downward falling plasma, and they form the convection cell, just like what you see in a drought picture in a soil. They are essentially similar, like, although the physics in the two cases may be very different. So, and these have typical size of about 1 megameter. So this is an example from, this is a cut from the whole thing. So you'll have 100 cells in the simulation that I'm describing. So the density, as you see that this is like a power law, and it falls somewhat in a shallow fashion in much of the domain, but very close to the surface, it falls extremely rapidly by orders of magnitude. And this makes this whole thing very challenging if you are interested on the surface. In many cases, one is not interested on the surface, and then you can just trim this whole part. But in order to resolve this top layer, one must have a sufficiently large number of grid points, at least a few per scale height. As you see, the scale height itself drops here very rapidly, right? That's the plot of the scale height, pressure and density scale height, that drops very rapidly. I didn't show the entropy plot, but you can imagine much of the domain, it's very close to adiabatic, just like the sun, very close to adiabatic. And it has outward radial gradient as negative, very close to the surface. That seems enough to initiate and drive the convection throughout the domain. That is all that is needed, and can actually transport much of the flux. So other than that, so as you see, these are the plots of various thermodynamic quantities as a function of depth. So so much of the variation is along the z direction, which is like the depth. Okay. We also impose some magnetic field, as you can imagine, that much of these dynamos, like solutions like here, which will typically give you a strength in its saturated state, no more than an equipartition. Typically not. Dynamo does not saturate at strengths much larger than the equipartition. So you'll be always around the equipartition strengths. Say these yellow and black here would mean that equipartition strength. So this might give you some initial large scale coherent field that might be needed still to go from here to the sunspot is a big step actually. It's not a small step. Just having that does not guarantee you the spot. So unless the surface, in our experience, unless the surface is very well resolved, so that's why these are the typical resolutions. For the Z resolution, we have 0.02 megameter is resolved. So we have same number of grid points, 1024, also in the Z direction, which is 4 times smaller in its extent. And very much to the bottom, as you see, the peak is towards the bottom, right? So Z, 0 is the bottom, 1 is the top, or minus 25 to 0, 0 to 1. So this is the bottom of the domain. This is the top of the domain. Towards the bottom of the domain, we impose some weak field. So beta square is normalized by the equipartition, the imposed field strength. And in the strongest case, we impose a field of about 25% level, which is very close to what you get from dynamo. So it's a horizontally inclined or horizontal field towards the bottom with a strength of about 20-25% in the strongest case, but we vary from 5% to 25%. We never impose a strong field, unlike many previous work where the strong fields are imposed in the bottom and sometimes they simply form a spot. So that is something that we purposely wanted to avoid. We don't want to impose a field to see a strong field emerging on the surface. So you can pretty much say that we're not imposing much and trying to see if there is any self-consistent formation of spot-like concentrations on the surface here. So that has been the goal of this work. The convection looks almost identically. As you go deeper in the domain, the convection cell size becomes larger and larger, something that you can easily understand by mass conservation, that it must be so, because your scale heights are dropping, density is dropping, And if you apply just the continuity, you will see that the granule sizes must actually vary like this. This is just some recap for the convection. I should not waste too much time on this. So you know that in the stellar physics language, one defines an adiabatic nabla. It's not an operator, it's an adiabatic nabla, which has a value gamma minus 1 by gamma. And if your gradients are steeper than this adiabatic gradient, that will be the condition for convective instability. This is exactly like a Schwarzschild criterion, if you are more familiar with the Schwarzschild thing, in which case ds by dz is less than 0, guarantees you a convection. Okay. For polytrope, this is the condition. So we are basically running with a polytrope, and which we can vary also. So a lot of experiments are done, but I'll only highlight. If you look at the velocity power spectrum at some depth, which is close to the bottom, so then you see that there is essentially the power dominates at the largest length scale. So this is the velocity power spectrum as a function of, say, wave number, and much of the power anyway lies in the largest sizes. And if you're familiar with Shravan's work, Shravan has been working a lot and very interesting problem of convection conundrum, which I believe is very interesting problem. And I will not have time to discuss some interesting ideas that have emerged in terms of the Deerdorf flux, that whether the convection is driven by heat from below or just by cooling from top. And these two scenarios can give you very different velocity power spectrum, because in the other scenario, when you are cooling from top, in terms of, it's just like if I take a heat out from the surface from this location, the delta S or the entropy change will be inversely proportional, or in some sense negative, of the density. So that will mean that this part will become more dense and will fall below under the gravity. That is all there is in some sense. And they will further and further shrink because they are falling further into the denser and denser environment. So downdrafts become narrow while upwellings are broad. And this gives you a very interesting picture of entropy rain in which large scales are not even excited. So you can actually drive all the convective flux only by these falling cool drops instead of upward hot blobs. And that's basically a very detailed picture. But in case you are interested, you can go back and look at this. It's a very interesting paper. An idea called entropy rain. That could be an alternate. And we have been running even this entropy rain based convection model, also in context to the spot formation picture. That picture remains largely same or similar, but convection itself is changing, because in that case, this power at the larger scale is not even excited. So you will get something that looks more in which much of the convection velocity power remains at the large wave numbers or small length scales, something that Shravan has reported. So these are very interesting ideas on convection, regardless of the magnetic field. Just wanted to briefly mention. Nevertheless, regardless of this convection, in these setups, we do find that on the surface, while there is nothing imposed on the surface, absolutely nothing imposed in terms of the vertical magnetic field, you see that the large concentrations have formed. There are many examples actually. So this is how the simulation looks. This is what is shown in this image, for example, is the vertical magnetic field Bz in units of equipartition strength, which you can see is actually saturated at levels of 2.5 or 2. So it's at least 2 times larger than the equipartition. So typically strong fields, 1 to 5 kilogauss fields.
Nishant,
yes?
Sorry to interrupt, but if you can wrap it up as quickly as possible.
Yeah, okay, no problem. Yeah. So you can see, basically the point was that with higher and higher resolution, and that had actually in this particular case played a role. With smaller resolution, one couldn't have captured this very surface physics. And these structures have simply just formed there. So in a very, with the time constraint, this is all I can say, that there is these spots that are naturally forming without any strong field imposed in the domain. There is no field that is imposed that is way stronger than any of these. Physical mechanism is not fully understood, but we are still investigating. The flux emergence seems to be linear in type process. So it's not looking like an instability. There are other ideas. So there are some questions. And these questions are the questions from the times that the sunspots are known, basically. What is the mechanism causing these concentrations? What determines their sizes? Is it due to NEMP? Because NEMP has been a thought in at least the pencil code community. And it's a very interesting thought. But somehow in our simulations, we seem to rule out that the NEMP is most likely not operating in our simulation. So we further need to look for other alternate mechanisms. So I'm currently investigating and somewhat confident that there is an important role played by turbulent diamagnetism that is basically leading to a variety of sunspots. If you look at the sun on any regular day, you will find that the sunspots don't have a very particular feature. They just come in all types of varieties, different sizes are there, different time scales are there, different field strength, or some are just like some little features. So there are various varieties. So nature seems to offer variety. So there's some don't have umbra, penumbra and stuff. So all types of varieties are possible. And I'm essentially investigating what is it, one feature or one key physical mechanism that might be controlling this type of variety. Why there is so much variety if everything is just dynamo, which might be operating in a single or some activity belt. Anyway, so there is more. So these sizes in the box, in these boxes, typical sizes are 10 to 15 megameters. So these are not small spots, by the way. So one granule is only 1 megameter. So these are definitely much larger scale structure compared to the convection granule. We are investigating some PDFs, and so maybe I'll skip that. Interesting thought about the effective pressure, which we believe is not the one that is working in our case, is that you can simply define your turbulent energy in terms of rho u square plus b square by mu, and turbulent pressure as only difference is factor half here, except 1/3, which doesn't matter. So this turbulent pressure you can write in terms of turbulent energy minus something. So it's very, very interesting. So if your total energy is conserved, which is the case in this case, having a small scale magnetic field will lead to a reduction in the turbulent pressure. And if that is strong enough, you can argue that it can even lead to effectively negative. This is a very simplistic isotropic type picture. In reality, it is much more complex. But you can envisage just from this that the effective pressure can turn negative. And if that is so, it can actually lead to an instability that might lead to, it's like a suction effect. It just sucks all the small magnetic field elements from the surrounding and forms a big monolith like.
I think Nishant, we should wrap it up so that we have some questions.
Okay.
Time for some questions, please.
Yeah. So just last half a minute. So this basically was the idea which we thought is not working because of some other argument. So diamagnetism, I just leave it here if somebody asks questions. So yes, so the conclusion is we do see spontaneously forming flux concentrations in these simulations. Typical strengths are like this and sizes are like this. So there is a variety in the simulations. And I don't know, these may be like progenitor-like things to the actual sunspots or active regions. So thanks.
Thank you, Nishant. It was a very, very nice, detailed explanation of how sunspots are actually happening. I think let us have the round open for some questions. In case if someone has a question, please raise your hand so that I can basically unmute, and then we can go ahead. Any questions to Nishant?
So I have a question. So I can't seem to be able to raise my hands, but anyway, whenever it's the queue, when I get a chance, just let me know.
No, Dipendra, you can start, please.
Okay. So Nishant, nice talk. So I have a question, which is kind of something that bothers all of us, I guess. So one of the major issues in the understanding of the formation of sunspots is this conundrum on whether a sunspot forms from the rise of a coherent omega-like flux tube from the deep interior of the convection zone, or does it come together from a collection of more fragmented fibril-like flux tubes in the near surface layers? Is there a way that these simulations can actually resolve that impasse?
Yes, I would say, and as you can see that it will depend on what is the scenario in that particular simulation. So for example, in this simulation, the Parker instability is not excited because there is no very strong field imposed at the bottom. And that is the reason that we didn't want to impose any strong field. And therefore, the omega-like picture does not seem conducive in these models, in these simulations. And then it is mostly, and that's what I meant by this diagram, because there is some sort of a pumping of small scale field elements that are pumped towards, say, the edges. So I can maybe, if I can go back somehow. I don't know how to go back in this. Yeah. So in many cases, this is one, if you can still see my screen.
Yes, we can see your screen.
So in many cases, you can see this is super granule-like structure, and the fluxes are concentrated at basically the nodes of these, basically in the downdraft lanes. And that's what I meant to actually highlight in some of these, that if you go to somewhat deeper layer in which the convection cell sizes are getting larger and larger, your downdraft lanes are becoming thicker and thicker. Magnetic fields that you are seeing at the surface, which are these white things here, that seem to be co-spatial to the downdraft lanes of the basically the downdraft lanes of a deeper layer. In fact, that's what, in my opinion, also controls the size of the sunspot. So I would simply argue that this is essentially in these models or in this simulation, a flux expulsion from region of high turbulent intensity to low turbulent intensity. In that sense, the diamagnetic pumping of the small scale field elements that are anyway present are simply being pushed out towards the periphery of the convection cell. So in this case, there is no omega loop even possible because the Parker instability is not excited.
Okay, we have one more question. Yeah, thanks, Dibyendu. We have one more question from Kandu. Kandu, I've asked you to unmute.
Yeah, I think, nice, Nishant. Every time I see this picture,
yeah,
I get impressed. And this turbulent diamagnetism, I mean, you want to form a spot. So are you thinking things are in the intersection of this stuff? Where is the spot? Because if you are saying just now, as you explained to Dibyendu, that you're expelling from some updraft to downdraft, the downdrafts are all in rings, it looks, no?
Yeah, so downdraft, so you see, if you simply were to take a cut, so this is at a deeper layer, this is like 19 megameter. Now you go to 25 megameter. So you simply take, say, a vertical tube from here above. So these fields get strong, and then they, so there are these, so I did do this, what do you say, how to say, yeah, so horizontal gradients, if you apply on here, so it is basically taking the horizontal magnetic field, which is imposed Bx or By, and then turning it into a Bz type component. And that Bz is basically like unfolding here. So that unfolding is happening here. And then this field, I don't have a very nice paraview type plot. That is what I'm currently struggling. So this unfolding seems to be that as the fluxes are being expelled in a deeper layer, they are unfolding and basically appearing at the size corresponding to the downdraft of the deeper layer. They simply pop up at the surface, essentially like this. So at the surface, they look like this. So if you were to take a size of this spot here on the photosphere, 15 megameter is essentially the thickness of the downdraft lane at the deeper layer, like 19 megameter. That's what I'm trying to say.
Okay. And you see, this turbulent diamagnetism gets corrected if you have Lorentz forces.
Yes,
yeah. So
anyway, I actually wanted to show something more spectacular. So I ran some model last night, but it didn't come out successful. So I
Okay, thanks a lot. Thank you.
Nothing works at the last moment, Nishant.
No. It has been working for me for quite many years. This time it didn't work.
Okay, fair enough. Thank you so much for the questions. Nishant, you have some more questions at the Slack. I would request you to answer them on the Slack itself.
Thanks.
While we go to the next talk, the last talk of this session by Saurav Chatterjee from TIFR. Saurav, I've made you the co-host. Could you please share your screen?
Hello. Am I audible?
Absolutely well. Saurav, you are audible. We can hear you, Saurav.
Yeah, I'm just. Hello. Just 1 second. I recently updated my Mac, and now it has new permissions I need to give.
Fair enough.
Looks like I need to tweak and reopen. Huh.
Okay.
Okay, I will tweak and reopen.
Okay, in the meantime, we can continue our discussion. In case any more questions to Nishant, or anyone wants to raise their hands to ask something to Nishant or other speakers as well, as we are waiting for Prateek, I asked to unmute. Prateek, please go ahead.
Yeah, that was a very nice talk, Nishant. So what is this NEMP? Is this just the rain that you're talking about?
No. So those are totally different things.
I see.
Sorry.
Yeah, that rain thing is quite interesting, actually. Somehow I was focused too much on NEMP.
No, so NEMP is actually an idea where, as I just tried to show from a very isotropic-like example, but if you write the full Maxwell tensor, you can show it even more clearly, that the effective pressure you can write as 1 minus some parameter.
Okay, I'm back.
Yeah, just 1 second. Saurabh, Nishant is answering his last question, then I can switch on to you. Yeah, please, Nishant, sorry.
Yeah, no, so this NEMP is basically that if you consider your total turbulent energy to be constant, you can still make your effective pressure as negative, because that turns out to be just 2 times the total energy minus b square by 2. So having a small scale magnetic feature or small magnetic elements reduces the effective pressure.
Okay. Yeah.
So that reduction,
turbulent diamagnetism investigated by Nigel Wise and so on.
I have actually been following those works.
Thanks. I think that's good enough for me.
Thanks.
Okay, thank you so much, Nishant and Prateek. Now we go to the next speaker, Saurabh. Saurabh will be giving a talk as the last speaker for this session, and his talk is on numerical modeling for large N-star clusters. Saurabh, over to you. You have to unmute, Saurabh.
Yeah. Can you please confirm that you were seeing my title slide?
We can very well see your title slide and hear you well. Please go ahead.
Okay, great, thank you. So good afternoon, everyone. And first, I'd like to thank Dipanjan and other organizers for this workshop. Usually, we come under the umbrella of individual science cases, but it is excellent to come under the umbrella of computing for a diversity of science cases. Especially in today's astrophysics, the observational data are becoming more and more detailed, which allows us to probe more and more details in our models. And as a result, the models become very complex, and we really need numerical techniques to understand the data. It's not anymore a matter of choice. It's a matter of necessity that we need to get into computational aspects of astrophysics. So the plan of today's talk is kind of giving a brief overview of what we do when we try to model star clusters. So we have already heard several exciting talks about using computing for different science cases. So in my talk, I will be
talking about the science case of solving the gravitational n-body problem. But I will talk a lot about the gravitational n-body problem, but you will later see that there are a plethora of other physical processes that one must take into account to make the simulations realistic. So this is roughly the outline. What are star clusters? Why study star clusters? Then I will talk about the physical processes that we model. And then I will very briefly mention some of the numerical tools to study star cluster evolution. And very briefly, I will flash 3 results coming from our models in recent times. So star clusters come in various shapes and sizes and properties. Mainly, so it's very hard to distinguish all of the different star clusters using properties alone. There is a lot of overlap. But roughly speaking, there are these open star clusters, globular clusters, and nuclear clusters. And they have different ranges in masses and densities, typical ages, the binary fraction, and metallicity. And in particular, I will focus on globular cluster in this talk because you will see that these clusters have a very niche set of properties that make them very exciting for a large number of different studies. So the unique parameter space for globular clusters is they are old, they're low metallicity systems. All the stars roughly were born around the same time, if not exactly at the same time. And there are a large number of stars. So they are excellent factories for looking at exotic stellar sources, for example, as a result. So, for example, massive globular clusters are important targets in distant galaxies. So, if you want to constrain, for example, the galactic dark matter halo or the assembly history of the galaxy, you get a lot of constraints from exactly what is the age and radial spread of globular clusters. The typical old ages of globular clusters provide a direct window to early major star formation episodes in the universe. These are dynamically relaxed systems. If you don't know what that means, I will talk about it in a few slides. So that basically means that your results are not totally dependent on the initial conditions you choose. And it also means that these dense, dynamically relaxed systems are excellent factories for formation of stellar exotica, of a variety of stellar exotica. For example, gravitational wave sources, X-ray binaries, cataclysmic variables, short GRBs, supernova 1A, blue stragglers. So if you are interested in any kind of star that you cannot explain from its isolated singular binary stellar evolution, they are probably coming from dynamical processes that are happening inside dense star clusters. And a lot of people believe that all stars are born in clusters of some size, and the field stars, the so-called field stars, are also born in star clusters. So in some sense, you need to understand how star clusters evolve and dissolve and do a lot of interesting things while they are still bound. So let's take a look at the large N gravitational systems as a problem. It's a very special problem. Let me explain what I mean. So if you have a star of some mass, and then this is embedded in some distribution of other stars, let's say that the distribution of other stars is described by a density rho, then the force due to the masses in this annulus, let's say, is given by this quantity, but this M1 here is dependent, it goes up as R1 square. So as a result, the force ends up not depending on R at all. So the distance of this annulus from this star. So you can imagine that some other annulus that is at a different, larger distance from this annulus will have same contribution in the total force on this star. And that makes the gravitational in-body system special and also very hard to model. So imagine that you want to solve the orbit of a star that is sitting in a potential of other stars. Then, of course, the volume that is at a large distance from this star is much larger than the volume that is at a very small distance from the star. So most of the other stars that are creating the potential for this particular star is at a very large distance. So individual effects of two stars is small, but the overall effect from a large distance dominate compared to stars that are at a small distance. So as a result, you can think of the effects of the other star on that particular star as a relaxation process, okay? So this is what I mean. So two stars scatter each other, and the scatter, this is, of course, this movie is showing a very exaggerated scattering. Most of these scatterings are very small angle scattering. And the overall, the change in the orbit of that star happens on a very long time scale compared to the crossing time, okay? And the relaxation time is proportional to the number of stars in that system, okay? So the higher the number of stars, the slower this process happens. So as a result, what you are really interested in is a cumulative effect of a sequence of weak pairwise gravitational interactions. And this is a diffusive flow of energy from the center of the cluster to outskirts. So let's think about the energy flow a little bit. So if a star loses energy to another star due to this kind of scattering, then it actually sinks deeper into the potential because it's a bound system. So now it speeds up, and now it has even more energy to lose. And this, of course, is a runaway process. There is another way to think about it. So a cluster can be thought of as these two different areas. The central part, let's call it core. This is the outside core part. So the central stars are moving faster, so their effective temperature or average temperature is higher compared to the stars that are not near the center. So energy flows from center to outwards, but as a result, these stars become even hotter, so there is even more energy to flow, okay? So a natural consequence is mass segregation. So if you have a mix of stars, a mix of heavy and light stars, then the heavier stars lose energy and sink deep into the center. And the time scale for this sinking is given by this, okay? So for globular clusters, the crossing time is roughly 100,000 years. The relaxation time scale is about a gigayear. The age of the globular clusters is about 10 gigayear. So these are all relaxed systems. And the mass segregation time scale is given by the ratio of the mass that you're interested in to the average mass in the whole system times the relaxation time. So, for example, for black holes, this factor is 1/10, and this is about a gigayear. So over the age of a globular cluster, black holes will sink and do interesting things in the center for hundreds of times or hundreds of episodes of this. So what happens when these heavy stars sink to the center? the density becomes very high, and you can form binaries dynamically. We actually believe that the star clusters are born with a large number of primordial binaries, and the binaries having a higher cross-section readily interacts with other stars and binaries and higher hierarchical systems, and they make interesting systems dynamically. And of course, the time scale for scattering is hours to years. So you can see that the time scales that of interest can vary from gigayears to hours, essentially. The other thing that you have to take into account are single and binary stellar evolution. So there is a large range in mass for stars that a cluster is born with. And depending on the mass of the star, they will evolve over million years to gigayear timescale. Okay, and then of course every cluster is sitting in the potential of its host galaxy, so there will be tidal stripping of stars from the cluster by the galaxy, and you have to take that into account. Okay, so here I'm showing you the relevant timescales for each of these different processes that you have to take into account, and you can see that they are diverse timescales that you have to resolve. Okay? So let's talk about some of the numerical techniques. So the earliest understanding of gravitational n-body problems was came from its analogy to, say, ideal gas or thermodynamical systems, and it was understood that large n systems are are well approximated by the Fokker-Planck equation. So in principle, you can solve the Fokker-Planck equation and understand exactly how the cluster is evolving under two-body relaxation. But in the Fokker-Planck method, there is no way you can model all the other different important physics that are not happening on a relaxation timescale. The most most detailed method, of course, is the so-called direct n-body. Here you have individual stars and binaries, and you are tracking the individual gravitational pulls between each stars and binaries. And since you are solving all the forces, and at any given time, you always have the stars and the binaries, you can put in a lot of these different physics layers on top of the two-body relaxation. Okay, but it, of course, is very expensive. There is another method that has been very successful in modeling large n star clusters, like globular clusters, is called the Henon-type Monte Carlo. So let me get into the details of how the basic steps of a Henon-type Monte Carlo code looks like. You start from an n-body model. By n-body model, I mean you have the star masses and their position vector and velocity vector. And then you say that, okay, my cluster is spherically symmetric, and I don't really care about, to solve for the potential of the cluster, I don't really care about the exact position of the star. Instead, I will just distribute the star in a spherical shell. Okay, so you spread all the masses in spherical shells, you calculate the energy and angular momentum for all the stars in their orbit. And then you say that this is the magic of what Henon found in a conference paper. Actually, he never published that paper. And that allows us to actually model these systems more easily. You can approximate the total effects of many weak flybys encounters by one single super encounter. Okay, so essentially what we're saying is that all the random steps in the energy and angular momentum space a star is doing
You collect them over a fraction of a relaxation time scale, and you say that I want only the overall effect during that time, and it's possible to approximate that using a single superencounter. So once you have done that, that updates the energy and angular momentum, and then you calculate the new orbits given this energy and angular momentum. Now, of course, starting from an n-body model, you lost the n-body model during this phase because you don't have specific velocities and positions up to this stage. But once you have the energy and angular momentum of each star, you can Monte Carlo the new positions and velocities in these orbits that will be a solution of this energy and angular momentum to get back the new n-body model. So here you are probabilistically distributing the stars that are consistent with the updated energy and angular momentum. And as a result, you get back that n-body model. So throughout this process, you have advanced the cluster dynamically due to two-body relaxation. And you started from an n-body model, you obtained an n-body model, and then since you again got back stars and binaries, you can add physics as you wish. You can add strong scattering, for example, stellar evolution, tides, everything that you want to do. And then, of course, you repeat this over and over. So Fokker-Planck cannot access these physical processes. Henon-type Monte Carlo can access all physical processes that direct n-body can access. Of course, the need to use Henon-type Monte Carlo is that it scales very well with n. So as you increase n, it becomes very quickly it becomes impossible to run a direct n-body model. So let me just show you very quickly how the approximated method compares with the direct n-body method. So here I'm showing you the 1%, 10%, 50, 90, and 99% Lagrange radii as a function of time. Red is coming from direct n-body, black is coming from Monte Carlo, and you can see that the Lagrange radii, that basically tells you how the mass is distributed throughout the cluster, they compare reasonably well with direct n-body, and significant difference you see is only near the tidal boundary, where the assumption of spherical symmetry becomes a little limiting. Of course, the fun in this is the n-body model was run over 160 CPUs and 16K GPUs for over a year, and the black lines were generated in 2 days on only 48 CPUs. So after we run this model, we basically end up getting star by star properties. So we have all the stellar and binary properties, all their dynamical properties, and all their stellar and dynamical history throughout the age of that particular cluster. So you can do a lot of really nice science. You can solve a lot of different science goals. You can directly compare your model with observations, and you can look for different exotic stars, etc.
Saurabh?
Yeah.
Sorry to interrupt, but could you quickly wrap it up? You've already run out a bit of time.
Can I have 2 minutes?
Yeah, one. Let's try one. Okay. Quickly.
So this is just an example of what is achievable. For example, I'm taking a model and creating an HR diagram. You see blue straggler stars, red giant, main sequence, binary sequence, white dwarf cooling, etc. You can do direct comparisons with the globular clusters. For example, this is just an example of NGC 6293. So the dots are data, and we can create the surface brightness profile, the velocity dispersion profile. Here is a particular example. It's not only, we can go into a lot of details and in using these models.
For example, here I'm showing you the comparison between the RC over core radius to half-life radius as a cluster mass. The circles are observed systems. The field circles are from models, and you can measure the mass segregation between different mass species of stars. And if I compare the models, the mass segregation calculated from the models with the observed mass segregation from globular clusters, we see excellent agreement. Although it was not, it wasn't the simulations were not generated to do this. Using mass segregation, of course, we could infer the number of black holes in any particular cluster. For example, we did it for 50 ACS globular clusters and calculated how many black holes could be in these clusters. And of course, we had a lot of fun trying to explain the gravitational wave detections coming from binary black hole mergers. And most recently, after the LDK release of the merger rate as a function of redshift, we found out that using our models, the predicted rate, that's the brown line, that compares really well with the with what LDK thinks to be the merger rate in the universe. And in fact, the observed rate can entirely be explainable by the globular clusters. Because we are running out of time, I'll just put the summary slide here and stop.
Thank you so much, Saurabh. It was a very, very nice overview of the N-body codes and simulations. I think I will ask the audience and the participants to raise their hands so that they can answer so that they can pose a question. I think there is already one question on Slack, Saurabh, if I actually can read it out to you.
Yeah,
so it is by Sandeep Kumar Kataria, and he says that in Henon type Monte Carlo method, how do you make sure multiple flyby mimicked by superfly effects are similar? Which parameter can tell about the accuracy of this technique?
So we did a lot of comparisons with direct N-body results. So we take exactly the same initial cluster, run it using direct N-body, run it using Henon type Monte Carlo code, and compare the results. So I'm probably going into a little bit too much details. So there are some things that you need to investigate a lot. For example, so the accuracy depends a lot on how accurately you can calculate the diffusion coefficients. If you know the Fokker-Planck methodology, you know that everything depends on the diffusion coefficients and their values. So I can probably give a long answer if you.
Maybe we can restrict to 1 or 2 minutes. Is fine. Okay. Yeah. So are there any more questions to Saurabh? If not, then we can open slightly for, there's one unanswered question. Let's see. Where is this one unanswered question? Okay, so there is one. Okay, Saurabh, I think there are no more questions to you personally, but as a host, I can actually take the privilege to ask you. I'm going to say I've been following the N-body codes, how they progress, and they have done spectacular when it comes to scaling in these large clusters, especially CPU clusters. Where do you think that how will N-body code with this prowess that it has to basically scale very well? Could it now do a competition or a complementary to real fluid codes, or do you see that it's still a challenge for N-body codes?
Let me not directly answer the question that you were asking. I'll answer the question with another question. why would you even want to do it? So the reason why you want an n-body code to solve the dynamically relaxed systems is that you really need it. You have a collision term that you need to solve. In cases of galaxies, for example, where the fluid codes are mostly used, or cosmological simulations, they are not relaxed systems. There is no sync term that you have to think about. So it's actually better to use the tools that they are using. Now, what can be the way forward, I think, is some hybrid approach, and a lot of people are already trying to do that. So you start from a cosmological simulation, and then people like Fire or Illustrates, they are doing zoom-in simulations. So you can do a zoom-in, and you have a collection of galaxies, and you have all the details of how exactly the galaxy formed, how its tidal field evolved, etc. And then you can take any one of these galaxies, and then you say that, okay, in this galaxy, I have, say, 100 globular clusters. And then how do I evolve the globular cluster in an evolving tidal field? That, I think, is the way forward. And I'm totally happy with having the type of simulations that they are doing already, and then inserting n-body simulations using their thing as constraints.
Yeah, I think yes, you are right. The hybrid is the way forward, and it's a very interesting thought that you have put up. So I think I will take one last question, which was already posted on Slack for this discussion session. We do not have much time, but I can take one before I end this session. So this is to Nishant. If you are online, Nishant. Nishant, this is a question from Meera Nandakumar. She says that for the velocity power spectrum plot, I can see a slope change. Is there something happening over there? Usually for density power spectrum, such slope change indicate transition between 2D and 3D turbulence. I was wondering, is similar thing happening there?
No, so I just basically with a direct message, I responded to that.
Okay.
I think this is just being a cuboidal box. So Kolmogorov type spectrum is essentially picking a forcing scale, which is limited by the vertical extent, which is smaller in this case. And therefore, you don't see, so it's like excitation or the energy injection scale is governed by the KH corresponding to the vertical extent, which is 4 times smaller. So that's why you don't see further excitation and hence flattening.
I see. Great. Thank you so much. And first of all, I would like to thank all the speakers of this session. It was a wonderful session where we learned a lot of things about the updates on using computational methods for solar and stellar physics. I would also urge all the speakers of this session as well as the previous sessions to please follow the Slack. Participants are writing out questions so that, or you can answer them directly, or you can answer them on Slack so that it can benefit all the other participants as well. The next session will be on numerical simulations of galaxy and extragalactic scales. That will be chaired by Sharanya. And we will start this session. The YouTube link will be online at 2:30. And we will start this session at 2:30. But just 15 minutes before, you all can join the Zoom thing. And right now, we will just break for lunch for an hour. And at 2:15, we reconvene back for the third and the fourth session on the computational astrophysics workshop. I once again thank all the speakers, thank all the participants as well to participate in these 2 sessions. And I look forward for their participation and enthusiasm even in the next 2 sessions as well. So we will break here for lunch. Zoom link is on. Basically at 2:15, we will reconvene again, and the YouTube link will be starting at 2:30. Have I missed anything, Dipanjan, Sharanya? If you want to add?
No, that is all. The YouTube stream of the previous stream has ended. So a new live stream will start at 2:30. So the previous stream has ended. That's just to announce people.
Okay. Unfortunately, we cannot have discussions over lunch.
Yeah, that is something we miss out with this online.
I can see that the Slack has been quite useful, and there is some vibrant chatter on Slack, which is very nice to see. Yes. And Saurabh, you also had a question from Sandeep Kataria on Slack. It's a very more technical question. I'll let you just respond to that on the Slack itself. in the channel session 2 channel.
Yeah, I think
Okay. Yeah, I'll do that.
Yeah,
I'll do that.
Yeah, exactly.
Thank you.
So yeah, so we will break here for an hour and we'll reconvene back at 2:15 for session 3 and session 4. And I'll make Sharanya the host. Okay.
Okay.
Thank you, everyone. Please stay tuned for the session 3 and session 4. We'll break here for 1 hour.
Okay, sound testing for YouTube stream, session 3. Sound testing for YouTube stream, session 3. Atharva, speak something there so that we'll know that the. Sound testing for YouTube, stream 3. Okay, testing 1, 2, 3. Testing for YouTube live 1, 2, 3, session 3. Testing. what are the mic auxiliary audio?
This is for mic.
This is for mic.
We want to keep it disabled for now.
No, Alsa has stopped.
Okay. Now I have mute Alsa and I have kept this on.
Okay, let me do the Skype test again. Testing Skype. 1, 2, 3. Testing. No, it's still not working. Testing Skype. 1, 2, 3. Testing. So it's not even showing a sample rate.
Yeah, I'll stop the streaming for a few minutes.
Okay.
Maybe then all the settings will be accessible.
Okay.
This is not getting active.
No. So it just muted. It's from Zoom. Somehow Zoom is accessing my desktop audio. Why is that?
So we have given Zoom permissions to access audio. That is why only it is able to pass on the speaker. But what it is doing is it is also picking up the microphone.
Yeah. And so is it because of OBS as well? Is OBS picking up the microphone?
Yeah, both of them are picking up. That's the problem. So desktop audio is.
What about active sources only? What is that? No, bottom.
Okay. Hello? No.
Okay, start this. Hello, check, testing.
Hello.
No, it's still not started.
The levels are changing. Yeah.
Hello. Yeah, the levels are changing, but is it directing it to the?
Is the Zoom unmuted there?
Yeah. Okay, testing 1, 2, 3, testing. Testing YouTube stream 1, 2, 3, testing. Testing YouTube stream test audio. YouTube stream test audio 1, 2, 3, testing. Testing YouTube stream audio 1, 2, 3, testing. Testing. Testing end.